Tonight we're not chasing dramatic rain footage or studying satellite loops of swirling storms. We're doing something quieter, opening an attendance sheet for the atmosphere. The monsoon isn't about non-stop downpours or apocalyptic flooding, though those things can happen. It's about a seasonal reversal of winds, a shift in where rising air and rain prefer to gather, a predictable reorganisation of pressure patterns that happens year after year. Each monsoon simply clocks in and clocks out. Pressure patterns adjust, winds reorganise, and humid air starts showing up more often, over land instead of lingering over the ocean. It's a routine event in the planet's calendar, documented and logged like any other recurring appointment. The attendance book starts with a simple observation. Land and ocean don't respond to sunlight in the same way. This uneven heating becomes the first line item in understanding how monsoons form. Land heats up quickly when the sun shines on it. Dark soil, rocky surfaces, bare ground, they all absorb solar radiation efficiently and warm the air directly above them. When the sun sets, or the season changes, that same land cools down just as fast, radiating heat back into space. The ocean, by contrast, is a more patient participant. Water has a high heat capacity, meaning it takes a lot of energy to raise its temperature even a little. Sunlight penetrates deeper into the ocean, spreading warmth through a thicker layer rather than concentrating it at the surface. The result is that oceans warm slowly and cool slowly, maintaining relatively stable temperatures across the seasons. In the pre-monsoon months, strong sunshine beats down on large continental areas, especially in the subtropics and tropics. Places like the Indian subcontinent, the Tibetan Plateau, the interior of West Africa, and the high deserts of North America absorb that sunlight and turn into enormous heat sources. The ground gets hot, the air above it gets hot, and pressure begins to drop. Meanwhile, the adjacent oceans remain cooler, and their pressure stays higher. In the attendance metaphor, heated land is the first box to get a check mark. The system is beginning to wake up. Air doesn't sit still when pressure differences develop. It moves from regions of higher pressure toward regions of lower pressure, always trying to smooth out imbalances. As land heats and pressure over continents drops, while pressure over adjacent oceans stays higher, a horizontal pressure gradient forms. This gradient isn't a sudden jolt or a violent push. It's a gentle, large-scale rearrangement of where air prefers to flow. The stronger the heating, the stronger the gradient. The stronger the gradient, the more insistent the push from ocean toward land. On the attendance sheet, the pressure difference column gets a quiet tick. The setup is complete, and now the flow can begin. Before the monsoon arrives, prevailing low-level winds might flow from land toward ocean, or they might run parallel to the coastline, depending on the season and the region. In South Asia, for example, the wintertime winds are dry northeasterlies that blow from the cold interior of the continent out toward the warmer Indian Ocean. In West Africa, the dry season features winds from the Sahara pushing southward. But as the pressure gradient builds with the coming of summer, those winds gradually reverse. They don't flip overnight. The transition takes weeks. But once it happens, the new pattern is unmistakable. Moist onshore flows replace the dry continental breezes. In South Asia, the winds turn from dry northeasterlies in winter to moist southwesterlies in summer. This change is like employees switching shifts on a schedule. One flow checks out, the opposite direction checks in. The attendance log notes the reversal, and the monsoon season is officially underway. The ocean is a huge reservoir of moisture, and when winds start blowing from sea to land, they carry water vapor inland. This is the raw material for clouds and rain. As the air travels over warm surfaces and encounters rising terrain, mountain ranges, plateaus, escarpments, it lifts, cools, and condenses. The moisture that was invisible as vapor becomes visible as clouds. In the attendance book, moisture is a separate column. Once the onshore flow has enough length and warmth, once it's been blowing steadily for days or weeks, the humidity box is considered present. The system now has fuel. Heated land doesn't just lower surface pressure, it also makes the air above it buoyant. Each day, especially in the afternoon when the sun is strongest, parcels of warm air rise from the surface. As they rise, they cool, and if they contain enough moisture, that moisture condenses into clouds. This daily convection is a routine process, happening over and over again throughout the monsoon season. With the monsoon moisture supply in place, these daily convection cycles become more frequent and more organised. The pattern is predictable. Sun heats land, air rises, clouds build, showers and thunderstorms form, rain falls, and then the storms decay as the sun sets and the surface cools. The logbook records this as a repeated daily attendance of afternoon convection. It's not chaotic, it's rhythmic. Within the larger monsoon pattern, there are features that help organise the storms. Monsoon troughs are elongated regions of low pressure that form over heated continents and nearby seas. These troughs act like organisational lines on the attendance sheet, gathering storms and enhancing the convergence of moist air. Rather than isolated thunderstorms popping up randomly across the landscape, the monsoon season features recurrent bands and clusters of clouds that line up along these troughs. The trough might sit in roughly the same position for days at a time, or it might shift slowly north or south as the season progresses. Either way, it provides a framework. The sheet now has an entry for organised low-pressure zone present. Storms know where to gather. Monsoon rainfall isn't just about surface winds and rising air, upper-level winds matter too. When air rises from the surface, it has to go somewhere. If the winds aloft are favourable, the rising air can spread out and escape horizontally, a process called divergence. This upper-level divergence creates a kind of vacuum that allows more air to rise from below, strengthening and sustaining the updrafts. If the upper-level winds aren't cooperative, if they block or suppress the outflow, then rising air gets capped and convection weakens. This upper-level pattern acts like support staff clearing space for new rising air to keep moving upward. On the log, a separate row tracks upper-level support. When it's present, convection has an easier time maintaining itself, and the monsoon rains are more robust. When it's absent, the system sputters. The South Asian monsoon is one of the most well-known examples, a classic tab in the attendance book. Pre-monsoon heating over the Indian subcontinent and the vast Tibetan plateau lowers surface pressure dramatically. The plateau, sitting at high elevation, acts like a huge elevated heat source, amplifying the thermal contrast. Moist air from the Arabian Sea and the Bay of Bengal flows inland as the low-level winds flip from northeasterlies to southwesterlies. The season progresses from south to north, with onset typically beginning along the southwestern coast of India in late May or early June, and then advancing northward over the following weeks. Withdrawal happens in reverse, starting in the northwest in September and retreating southward through October and November. In the file cabinet, this system has its own tab with expected arrival dates, typical progression maps, average rainfall totals, and year-by-year comparisons. The South Asian monsoon is so regular and so well documented that its onset and withdrawal are major events in the regional calendar, affecting billions of people. The West African monsoon involves a similar seasonal shift, but with its own regional character. Here, the Intertropical Convergence Zone, the ITCZ, a belt of low pressure and rising air that circles the planet near the equator, shifts northward over the African continent during the boreal summer. Moist southwesterly winds from the Gulf of Guinea move inland, feeding lines of thunderstorms and organised squall lines that march across the Sahel. As the ITZ migrates north, the region of frequent rain also shifts. Farmers and communities track this movement closely because it determines where and when the rains will arrive. On the attendance sheet, this system's tab shows a moving band of present rain days that tracks north in June and July, reaches its northernmost position in August, and then retreats south through September and October. The pattern is less intense than the South Asian monsoon in some ways, but just as vital to the people who depend on it. The North American monsoon is a more modest but very real pattern affecting parts of Mexico and the southwestern United States. Summer heating over the high deserts, the Mexican plateau, and the Basin and Range region helps draw moist air from the Pacific Ocean, the Gulf of California, and even the Gulf of Mexico. The result is a seasonal increase in thunderstorms, especially in the afternoons and evenings, across Arizona, New Mexico, and northern Mexico. These storms bring welcome relief from the intense heat and provide a significant portion of the region's annual rainfall. Though less intense and less extensive than some other monsoons, the North American monsoon follows the same checklist: heated land, change pressure patterns, onshore flow, and daily convection. It gets a smaller but very real attendance tab in the binder, with entries noting typical onset in early July and withdrawal by mid-September. Even once the large-scale monsoon pattern is established, storms often follow a regular diurnal cycle, a daily rhythm of building and decay. This is the monsoon clocking in each afternoon and clocking out at night. Morning hours are often quiet with partly cloudy skies and light winds, As the sun climbs higher and surface temperatures rise, convection begins to fire. By early to mid-afternoon, towering cumulus clouds dot the landscape and thunderstorms develop. These storms can produce heavy rain, lightning, gusty winds, and sometimes hail. As evening approaches and the sun sets, the surface cools, convection weakens, and the storms dissipate. Some storms propagate into the night as organized systems, but many simply fade away. From a logging perspective, the large-scale monsoon is a multi-month presence, but its rainfall often occurs in these predictable daily shifts. Each day's entries show similar patterns. Afternoon storms, present again. It's a recurring appointment kept reliably day after day. The monsoon doesn't last forever. As seasons change and the angle and intensity of sunlight decrease, the whole system begins to withdraw. Land surfaces cool more quickly than the ocean, weakening the pressure differences that drove the onshore flow. The thermal gradient that powered the monsoon reverses or disappears. Low-level winds gradually lose their moisture-laden inland direction and revert toward winter patterns. Dry air begins to dominate again. The attendance sheet begins marking early departures. Fewer rainy days appear in the log. The monsoon troughs weaken and shift. More frequent dry spells interrupt the pattern. Finally, the system returns to its off-season routine. Dry winds, stable conditions, and the oceanic moisture source cut off from the land. The monsoon has clocked out, leaving behind another column of data in the long record. The file is updated, the totals are calculated, and the system waits for the next cycle to begin. Monsoon seasons can vary significantly from year to year. This interannual variability is carefully tracked and studied. Some years show stronger pressure gradients and more abundant moisture transport, leading to above-average rainfall. Other years are weaker, delayed, or cut short, resulting in below-average totals and potential drought. Large-scale climate patterns play a role in these differences. El Niño, a warming of the central and eastern tropical Pacific Ocean, tends to weaken monsoons in some regions, such as South Asia, by altering atmospheric circulation patterns and shifting the location of rising air. La Niña, the opposite phase with cooler than average Pacific waters, often enhances monsoons in those same regions. Other factors, like the temperature of the Indian Ocean, the strength of high-altitude jet streams, and even distant weather patterns over the Atlantic or the polar regions, can influence monsoon performance. In the attendance metaphor, some years the monsoon is early and diligent, arriving on time and delivering abundant rain. Some years it's late, with onset delayed by weeks. Some years it's quiet, with weak circulation and disappointing totals. Climatologists keep long records of these variations, noting the anomalies and searching for patterns that might improve forecasts. Monsoon behaviour is tracked using a wide array of tools and measurements. Rain gauges scattered across the landscape provide ground truth, recording daily and seasonal totals at thousands of locations. Wind measurements from surface stations and weather balloons capture the reversal of flow and the strength of the onshore currents. Satellite observations provide a broader view, monitoring cloud cover, rainfall estimates, sea surface temperatures, and atmospheric moisture content. All of this data is summarized into indices, numerical values that capture the state of the monsoon at any given time. These data sets form a long historical attendance sheet showing onset dates, total rainfall, spatial patterns, and year-to-year variability. Scientists use these logs to study trends, understand the physical mechanisms at work, and refine seasonal forecasts. The file cabinet grows thicker over time, but the format remains familiar: dates, totals, anomalies, and quiet notes about what happened and why. For many regions, monsoon rains are essential for agriculture, reservoirs, and groundwater recharge. Too little rain can mean drought, crop failure, water shortages, and economic hardship. Too much rain can mean flooding, landslides, and damage to infrastructure. Yet in this story, we keep the focus on the pattern rather than the disasters. Monsoons are scheduled deliveries of water that communities have adapted to over centuries. Farmers time their planting to the monsoon's arrival. Water managers plan reservoir operations around expected seasonal inflows. Cities and villages have developed strategies for coping with both the abundance and the absence of rain. The attendance sheet has side columns noting crops, rivers, and reservoirs that respond to each season's performance. A strong monsoon might fill reservoirs to capacity and yield bumper harvests. A weak monsoon might strain water supplies and reduce agricultural output. The pattern is neither good nor bad, it simply is, and societies have learned to work within its rhythms. It's important to clarify the difference between individual storms and the monsoon as a system. A single thunderstorm can happen almost any time and anywhere if conditions are right. Heat, moisture, lift, and instability. The monsoon, by contrast, is a months-long shift in average winds, moisture availability, and pressure patterns. It doesn't guarantee rain every day. It simply increases the overall probability and organises the pattern. Some days within the monsoon season are dry. Some weeks might see little rainfall. But the large-scale setup remains in place, favouring convection and rain more often than not. On the attendance form, one row is today's storms, describing whether convection actually occurred on a given day. Another row is seasonal pattern in effect, noting whether the monsoon circulation is present. Both are logged, but they describe different scales. The monsoon is the framework. The daily storms are the individual events that occur within that framework. Scientists are studying how monsoons may change as the climate warms. This is a complex topic with many uncertainties, but some patterns are beginning to emerge. Warmer temperatures mean the atmosphere can hold more moisture, which might lead to heavier rainfall events during the monsoon season. At the same time, changes in land-ocean temperature contrasts, shifts in jet stream patterns, and alterations in sea surface temperatures could affect the strength and timing of monsoon circulations. Some studies suggest that monsoon onset dates might shift, arriving earlier or later than historical averages. Others suggest that the distribution of rainfall could change, with more intense bursts of rain separated by longer dry spells, rather than a steady, moderate pattern. The attendance sheet becomes a tool for noticing subtle drifts, onset dates shifting by a few days per decade, rainfall clusters changing in frequency, regional patterns evolving in ways that don't match the long-term record. Rather than declare sudden changes or jump to conclusions, the log collects year after year of carefully measured entries. Over time, trends become visible, and the cumulative data helps scientists understand what's changing and why. Monsoons are not chaotic intruders or unpredictable disasters. They are recurring shifts in the atmosphere's schedule, governed by sunlight, land-sea contrasts, and the physics of warm, moist air. Each year they arrive, stay for their allotted time, and depart, leaving behind another column of data in the long record. The process is as regular as the changing seasons, as predictable as the sun's path across the sky. There are variations, of course, some years stronger, some years weaker, some years early, some years late. But the fundamental pattern remains. The monsoon clocks in when the land heats up and pressure gradients form. It clocks out when the land cools down and the gradients weaken. In between, it delivers moisture, organises storms, and shapes the climate of entire continents. Picture a quiet office in the sky where winds and clouds sign in for seasonal shifts. The land sends up its request. We're hot now, we need moisture. The ocean responds, moisture is available, winds are reversing. The pressure gradient files its report, flow is established, convergence is active. The convection department marks its hours. Rising air reported, clouds forming, rain likely. Each day the afternoon shift arrives on schedule. Each evening the shift ends and the system winds down. Each week the totals are tallied. Each month the pattern is reviewed. And at the end of the season, the monsoon signs out, the winds reverse again, and the atmosphere returns to its off-season routine until the next cycle begins. The monsoon is not a storm, it's a season. It's not a single event, it's a pattern. It's not chaos, it's a schedule. And like any good schedule, it can be tracked, logged, and understood. The attendance sheet is simple: date, location, winds, pressure, moisture, convection, rainfall. Column after column, year after year, the data accumulates, the pattern repeats. The monsoon clocks in and clocks out as regular and reliable as the turning of the earth. Tonight we're not chasing dramatic rain footage or studying satellite loops of swirling storms. We're doing something quieter, opening an attendance sheet for the atmosphere. The monsoon isn't about non-stop downpours or apocalyptic flooding, though those things can happen. It's about a seasonal reversal of winds, a shift in where rising air and rain prefer to gather, a predictable reorganisation of pressure patterns that happens year after year. Each monsoon simply clocks in and clocks out. Pressure patterns adjust, winds reorganise, and humid air starts showing up more often over land instead of lingering over the ocean. It's a routine event in the planet's calendar, documented and logged like any other recurring appointment. The attendance book starts with a simple observation. Land and ocean don't respond to sunlight in the same way. This uneven heating becomes the first-line item in understanding how monsoons form. Land heats up quickly when the sun shines on it. Dark soil, rocky surfaces, bare ground, they all absorb solar radiation efficiently and warm the air directly above them. When the sun sets or the season changes, that same land cools down just as fast, radiating heat back into space. The ocean, by contrast, is a more patient participant. Water has a high heat capacity, meaning it takes a lot of energy to raise its temperature even a little. Sunlight penetrates deeper into the ocean, spreading warmth through, a thicker layer rather than concentrating it at the surface. The result is that oceans warm slowly and cool slowly, maintaining relatively stable temperatures across the seasons. In the pre-monsoon months, strong sunshine beats down on large continental areas, especially in the subtropics and tropics. Places like the Indian subcontinent, the Tibetan Plateau, the interior of West Africa, and the high deserts of North America absorb that sunlight and turn into enormous heat sources. The ground gets hot, the air above it gets hot, and pressure begins to drop. Meanwhile, the adjacent oceans remain cooler, and their pressure stays higher. In the attendance metaphor, heated land is the first box to get a check mark. The system is beginning to wake up. Air doesn't sit still when pressure differences develop. It moves from regions of higher pressure toward regions of lower pressure, always trying to smooth out imbalances. As land heats and pressure over continents drops, while pressure over adjacent oceans stays higher, a horizontal pressure gradient forms. This gradient isn't a sudden jolt or a violent push. It's a gentle, large-scale rearrangement of where air prefers to flow. The stronger the heating, the stronger the gradient. The stronger the gradient, the more insistent the push from ocean toward land. On the attendance sheet, the pressure difference column gets a quiet tick. The setup is complete, and now the flow can begin. Before the monsoon arrives, prevailing low-level winds might flow from land toward ocean, or they might run parallel to the coastline, depending on the season and the region. In South Asia, for example, the wintertime winds are dry northeasterlies that blow from the cold interior of the continent out toward the warmer Indian Ocean. In West Africa, the dry season features winds from the Sahara pushing southward. But as the pressure gradient builds with the coming of summer, those winds gradually reverse. They don't flip overnight. The transition takes weeks. But once it happens, the new pattern is unmistakable. Moist onshore flows replace the dry continental breezes. In South Asia, the winds turn from dry northeasterlies in winter to moist southwesterlies in summer. This change is like employees switching shifts on a schedule. One flow checks out, the opposite direction checks in. The attendance log notes the reversal, and the monsoon season is officially underway. The ocean is a huge reservoir of moisture, and when winds start blowing from sea to land, they carry water vapour inland. This is the raw material for clouds and rain. As the air travels over warm surfaces and encounters rising terrain, mountain ranges, plateaus, escarpments, it lifts, cools, and condenses. The moisture that was invisible as vapour becomes visible as clouds. In the attendance book, moisture is a separate column. Once the onshore flow has enough length and warmth, once it's been blowing steadily for days or weeks, the humidity box is considered present. The system now has fuel. Heated land doesn't just lower surface pressure, it also makes the air above it buoyant. Each day, especially in the afternoon when the sun is strongest, parcels of warm air rise from the surface. As they rise, they cool, and if they contain enough moisture, that moisture condenses into clouds. This daily convection is a routine process, happening over and over again throughout the monsoon season. With the monsoon moisture supply in place, these daily convection cycles become more frequent and more organised. The pattern is predictable. Sun heats land, air rises, clouds build, showers and thunderstorms form, rain falls, and then the storms decay as the sun sets and the surface cools. The logbook records this as a repeated daily attendance of afternoon convection. It's not chaotic, it's rhythmic. Within the larger monsoon pattern, there are features that help organise the storms. Monsoon troughs are elongated regions of low pressure that form over heated continents and nearby seas. These troughs act like organisational lines on the attendance sheet, gathering storms and enhancing the convergence of moist air. Rather than isolated thunderstorms popping up randomly across the landscape, The monsoon season features recurrent bands and clusters of clouds that line up along these troughs. The trough might sit in roughly the same position for days at a time, or it might shift slowly north or south as the season progresses. Either way, it provides a framework. The sheet now has an entry for organised low-pressure zone present. Storms know where to gather. Monsoon rainfall isn't just about surface winds and rising air. Upper-level winds matter too. When air rises from the surface, it has to go somewhere. If the winds aloft are favourable, the rising air can spread out and escape horizontally, a process called divergence. This upper-level divergence creates a kind of vacuum that allows more air to rise from below, strengthening and sustaining the updrafts. If the upper-level winds aren't cooperative, if they block or suppress the outflow, then rising air gets capped and convection weakens. This upper-level pattern acts like support staff, clearing space for new rising air to keep moving upward. On the log, a separate row tracks upper-level support. When it's present, convection has an easier time maintaining itself, and the monsoon rains are more robust. When it's absent, the system sputters. The South Asian monsoon is one of the most well-known examples, a classic tab in the attendance book. Pre-monsoon heating over the Indian subcontinent and the vast Tibetan plateau lowers surface pressure dramatically. The plateau, sitting at high elevation, acts like a huge elevated heat source, amplifying the thermal contrast. Moist air from the Arabian Sea and the Bay of Bengal flows inland as the low-level winds flip from northeasterlies to southwesterlies. The season progresses from south to north, with onset typically beginning along the southwestern coast of India in late May or early June, and then advancing northward over the following weeks. Withdrawal happens in reverse, starting in the northwest in September and retreating southward through October and November. In the file cabinet, this system has its own tab with expected arrival dates, typical progression maps, average rainfall totals, and year-by-year comparisons. The South Asian monsoon is so regular and so well documented that its onset and withdrawal are major events in the regional calendar, affecting billions of people. The West African monsoon involves a similar seasonal shift, but with its own regional character. Here, the Intertropical Convergence Zone, the ITCZ, a belt of low pressure and rising air that circles the planet near the equator, shifts northward over the African continent during the boreal summer. Moist southwesterly winds from the Gulf of Guinea move inland, feeding lines of thunderstorms and organised squall lines that march across the Sahel. As the ITCZ migrates north, the region of frequent rain also shifts. Farmers and communities track this movement closely because it determines where and when the rains will arrive. On the attendance sheet, this system's tab shows a moving band of present rain days that tracks north in June and July, reaches its northernmost position in August, and then retreats south through September and October. The pattern is less intense than the South Asian monsoon in some ways, but just as vital to the people who depend on it. The North American monsoon is a more modest but very real pattern affecting parts of Mexico and the southwestern United States. Summer heating over the high deserts, the Mexican plateau, and the Basin and Range region helps draw moist air from the Pacific Ocean, the Gulf of California, and even the Gulf of Mexico. The result is a seasonal increase in thunderstorms, especially in the afternoons and evenings, across Arizona, New Mexico, and northern Mexico. These storms bring welcome relief from the intense heat and provide a significant portion of the region's annual rainfall. Though less intense and less extensive than some other monsoons, the North American monsoon follows the same checklist: heated land, changed pressure patterns, onshore flow, and daily convection. It gets a smaller but very real attendance tab in the binder, with entries noting typical onset in early July and withdrawal by mid-September. Even once the large-scale monsoon pattern is established, storms often follow a regular diurnal cycle, a daily rhythm of building and decay. This is the monsoon clocking in each afternoon and clocking out at night. Morning hours are often quiet with partly cloudy skies and light winds. As the sun climbs higher and surface temperatures rise, convection begins to fire. By early to mid-afternoon, towering cumulus clouds dot the landscape and thunderstorms develop. These storms can produce heavy rain, lightning, gusty winds, and sometimes hail. As evening approaches and the sun sets, the surface cools, convection weakens, and the storms dissipate. Some storms propagate into the night as organised systems, but many simply fade away. From a logging perspective, the large-scale monsoon is a multi-month presence, but its rainfall often occurs in these predictable daily shifts. Each day's entries show similar patterns. Afternoon storms, present again. It's a recurring appointment, kept reliably day after day. The monsoon doesn't last forever. As seasons change and the angle and intensity of sunlight decrease, the whole system begins to withdraw. Land surfaces cool more quickly than the ocean, weakening the pressure differences that drove the onshore flow. The thermal gradient that powered the monsoon reverses or disappears. Low-level winds gradually lose their moisture-laden inland direction and revert toward winter patterns. Dry air begins to dominate again. The attendance sheet begins marking early departures. Fewer rainy days appear in the log. The monsoon troughs weaken and shift. More frequent dry spells interrupt the pattern. Finally, the system returns to its off-season routine. Dry winds, stable conditions, and the oceanic moisture source cut off from the land. The monsoon has clocked out, leaving behind another column of data in the long record. The file is updated, the totals are calculated, and the system waits for the next cycle to begin. Monsoon seasons can vary significantly from year to year. This interannual variability is carefully tracked and studied. Some years show stronger pressure gradients and more abundant moisture transport, leading to above-average rainfall. Other years are weaker, delayed, or cut short, resulting in below-average totals and potential drought. Large-scale climate patterns play a role in these differences. El Niño, a warming of the central and eastern tropical Pacific Ocean, tends to weaken monsoons in some regions, such as South Asia, by altering atmospheric circulation patterns and shifting the location of rising air. La Niña, the opposite phase with cooler than average Pacific waters, often enhances monsoons in those same regions. Other factors, like the temperature of the Indian Ocean, the strength of high-altitude jet streams, and even distant weather patterns over the Atlantic or the polar regions, can influence monsoon performance. In the attendance metaphor, some years the monsoon is early and diligent, arriving on time and delivering abundant rain. Some years it's late, with onset delayed by weeks. Some years it's quiet, with weak circulation and disappointing totals. Climatologists keep long records of these variations, noting the anomalies and searching for patterns that might improve forecasts. Monsoon behavior is tracked using a wide array of tools and measurements. Rain gauges scattered across the landscape provide ground truth, recording daily and seasonal totals at thousands of locations. Wind. Measurements from surface stations and weather balloons capture the reversal of flow and the strength of the onshore currents. Satellite observations provide a broader view, monitoring cloud cover, rainfall estimates, sea surface temperatures, and atmospheric moisture content. All of this data is summarized into indices, numerical values that capture the state of the monsoon at any given time. These datasets form a long historical attendance sheet, showing onset dates, total rainfall, spatial patterns, and year-to-year variability. Scientists use these logs to study trends, understand the physical mechanisms at work, and refine seasonal forecasts. The file cabinet grows thicker over time, but the format remains familiar. Dates, totals, anomalies, and quiet notes about what happened and why. For many regions, monsoon rains are essential for agriculture, reservoirs, and groundwater recharge. Too little rain can mean drought, crop failure, water shortages, and economic hardship. Too much rain can mean flooding, landslides, and damage to infrastructure. Yet in this story, we keep the focus on the pattern rather than the disasters. Monsoons are scheduled deliveries of water that communities have adapted to over centuries. Farmers time their planting to the monsoon's arrival. Water managers plan reservoir operations around expected seasonal inflows. Cities and villages have developed strategies for coping with both the abundance and the absence of rain. The attendance sheet has side columns noting crops, rivers, and reservoirs that respond to each season's performance. A strong monsoon might fill reservoirs to capacity and yield bumper harvests. A weak monsoon might strain water supplies and reduce agricultural output. The pattern is neither good nor bad, it simply is, and societies have learned to work within its rhythms. It's important to clarify the difference between individual storms and the monsoon as a system. A single thunderstorm can happen almost any time and anywhere if conditions are right: heat, moisture, lift, and instability. The monsoon, by contrast, is a months-long shift in average winds, moisture availability and pressure patterns. It doesn't guarantee rain every day, it simply increases the overall probability and organises the pattern. Some days within the monsoon season are dry, some weeks might see little rainfall, but the large-scale setup remains in place, favouring convection and rain more often than not. On the attendance form, one row is today's storms, describing whether convection actually occurred on a given day. Another row is seasonal pattern in effect, noting whether the monsoon circulation is present. Both are logged, but they describe different scales. The monsoon is the framework. The daily storms are the individual events that occur within that framework. Scientists are studying how monsoons may change as the climate warms. This is a complex topic with many uncertainties, but some patterns are beginning to emerge. Warmer temperatures mean the atmosphere can hold more moisture, which might lead to heavier rainfall events during the monsoon season. At the same time, changes in land-ocean temperature contrasts, shifts in jet stream patterns, and alterations in sea surface temperatures could affect the strength and timing of monsoon circulations. Some studies suggest that monsoon onset dates might shift, arriving earlier or later than historical averages. Others suggest that the distribution of rainfall could change, with more intense bursts of rain separated by longer dry spells, rather than a steady, moderate pattern. The attendance sheet becomes a tool for noticing subtle drifts, onset dates shifting by a few days per decade, rainfall clusters changing in frequency, regional patterns evolving in ways that don't match the long-term record. Rather than declare sudden changes or jump to conclusions, the log collects year after year of carefully measured entries. Over time, trends become visible, and the cumulative data helps scientists understand what's changing and why. Monsoons are not chaotic intruders or unpredictable disasters. They are recurring shifts in the atmosphere's schedule, governed by sunlight, land-sea contrasts, and the physics of warm, moist air. Each year, they arrive, stay for their allotted time, and depart, leaving behind another column of data in the long record. The process is as regular as the changing seasons, as predictable as the sun's path across the sky. There are variations, of course, some years stronger, some years weaker, some years early, some years late, but the fundamental pattern remains. The monsoon clocks in when the land heats up and pressure gradients form. It clocks out when the land cools down and the gradients weaken. In between, it delivers moisture, organises storms, and shapes the climate of entire continents. Picture a quiet office in the sky where winds and clouds sign in for seasonal shifts. The land sends up its request. "We're hot now, we need moisture." The ocean responds, "Moisture is available, winds are reversing." The pressure gradient files its report. Flow is established, convergence is active. The convection department marks its hours. Rising air reported, clouds forming, rain likely. Each day the afternoon shift arrives on schedule. Each evening the shift ends and the system winds down. Each week the totals are tallied. Each month the pattern is reviewed. And at the end of the season the monsoon signs out, the winds reverse again, and the atmosphere returns to its off-season routine until the next cycle begins. The monsoon is not a storm, it's a season. It's not a single event, it's a pattern. It's not chaos, it's a schedule, and like any good schedule, it can be tracked, logged, and understood. The attendance sheet is simple: date, location, winds, pressure, moisture, convection, rainfall. Column after column, year after year, the data accumulates. The pattern repeats. The monsoon clocks in and clocks out, as regular and reliable as the turning of the earth. But within this reliable framework, there are subtleties worth noting. The monsoon doesn't arrive everywhere at once, and it doesn't affect all places equally. Think of it as a progressive wave of atmospheric reorganization that sweeps across a region over the course of weeks. In South Asia, the onset begins in Kerala, on the southwestern tip of India, and then marches northward and northwestward across the subcontinent. The Arabian Sea branch brings moisture to the western coast and the western Ghats, while the Bay of Bengal branch feeds the eastern regions and eventually pushes into the Indo-Gangetic plain. Each area has its own expected arrival window, and meteorologists track these dates closely, comparing them to historical normals. A delay of even a week can have significant implications for agriculture, so the timing is logged meticulously. The attendance sheet for the South Asian monsoon isn't just one line, it's a series of entries for different regions, each with its own clock-in date. Similarly, The retreat of the monsoon is gradual and organised. The northwestern regions of India and Pakistan see the monsoon withdraw first, usually in early September. The winds weaken, the moisture supply dwindles, and the rains become less frequent. By mid-September, much of northern India transitions to drier conditions. Southern regions hold on to the monsoon longer, sometimes into early November. This phased withdrawal is tracked and recorded, with each region's clock-out date noted. The pattern is so consistent that farmers and planners can build their calendars around it, knowing when to expect the last significant rains and when to prepare for the dry season. The West African monsoon has its own geography of onset and retreat. The coastal regions of the Gulf of Guinea see year-round rainfall, but the monsoon's northward migration determines when the Sahel receives its rains. In a typical year, the monsoon rain belt reaches southern Mali, Burkina Faso, and Niger in June, progresses northward into July, and then begins to retreat in August and September. The exact position of this rain belt on any given week can mean the difference between a good growing season and crop failure. Villages separated by just a few hundred kilometres might experience very different rainfall totals depending on how far north the monsoon pushes. The attendance log for West Africa is spatial as well as temporal, tracking not just when the monsoon arrives but where the rain actually falls. In North America, the monsoon's geography is defined by mountain ranges and deserts. The Sierra Madre Occidental, the Mogollon Rim, and the ranges of southern Arizona channel moisture and create preferred zones for thunderstorm development. The cities of Tucson and Phoenix see a marked increase in rainfall during July and August, with afternoon and evening thunderstorms becoming a regular feature. These storms are often localized, dropping heavy rain on one neighborhood while leaving another a few miles away completely dry. The attendance sheet for the North American monsoon includes spatial variability at a fine scale, with rainfall totals varying dramatically over short distances. A weather station in the mountains might record several inches of rain on a given day, while a station in the valley below sees nothing. The mechanisms that drive these regional patterns are variations on the same basic theme. Differential heating between land and ocean creates pressure gradients. Those gradients drive winds. The winds transport moisture. Moisture plus heat plus lift equals clouds and rain. But the details matter. The shape of coastlines, the height and orientation of mountain ranges, the temperature of nearby ocean currents, the presence or absence of large lakes, all of these factors modify the basic pattern and create regional character. The South Asian monsoon is so intense partly because of the Himalayas and the Tibetan Plateau, which act as enormous elevated heat sources and also block cold air from the north. The West African monsoon is shaped by the Sahara Desert, the Gulf of Guinea, and the complex topography of the African continent. The North American monsoon is influenced by the Gulf of California, the Mexican Plateau, and the orientation of mountain ranges that guide moisture flow. There are also intra-seasonal variations within a single monsoon season. The monsoon doesn't deliver rain at a steady rate from onset to withdrawal. Instead, it pulses. There are active periods when the monsoon trough deepens, moisture surges inland, and rainfall is widespread and frequent. These active periods might last a week or two, bringing daily thunderstorms and soaking rains. Then there are break periods, when the trough weakens or shifts, moisture flow decreases, and rainfall becomes sparse. During a break, skies might clear for several days in a row, temperatures rise, and the landscape dries out. Then the active phase returns, and the cycle repeats. These active and break periods are a natural part of the monsoon's internal rhythm. On the attendance sheet, they appear as fluctuations within the overall seasonal pattern. Active phase, July 8th through 18. Break phase, July 19th to 25. Active phase resumed, July 26th. The monsoon is present for the entire season, but its intensity waxes and wanes. These intra-seasonal oscillations can be influenced by larger atmospheric waves that propagate around the tropics. The Madden-Julian Oscillation, or MJO, is one such wave, characterized by enhanced convection that moves slowly eastward across the Indian and Pacific Oceans. When the MJO's active phase coincides with the monsoon region, it can enhance rainfall and trigger an active period. When the MJO's suppressed phase arrives, it can initiate a break. Forecasters monitor the MJO and other tropical waves to anticipate these shifts and provide advance warning of heavy rain or dry spells within the monsoon season. The attendance log gains another layer of detail. Not just whether the monsoon is present, but what phase of its internal cycle it's in. The relationship between monsoons and topography deserves closer attention. Mountains don't just sit passively in the landscape, they actively shape the monsoon. When moist air encounters a mountain range, it's forced to rise. As it rises, it cools, and moisture condenses, producing clouds and precipitation on the windward side of the range. This is called orographic lift, and it's a powerful rainfall enhancer. The Western Ghats in India, the Khasi Hills in northeastern India, the highlands of Ethiopia in East Africa, the Sierra Madre in Mexico, all of these ranges experience intense monsoon rainfall because of orographic lift. Some of the wettest places on Earth are located on the windward slopes of mountains in monsoon regions. Mawsynram and Cherrapunji in India, for example, receive staggering amounts of rain during the monsoon season, with annual totals often exceeding 10 metres. The leeward side of the range, by contrast, sits in a rain shadow, receiving much less moisture. The air has already lost much of its moisture on the windward ascent, so the descending air on the leeward side is drier and warming. The attendance sheet has separate entries for windward and leeward zones, reflecting these dramatic differences. Monsoons also interact with large bodies of water beyond the oceans. In South Asia, the Bay of Bengal acts as a moisture reservoir and a region of active storm development. Low-pressure systems and depressions frequently form over the bay during the monsoon season, drawing in moisture and then tracking westward or northwestward across India, bringing widespread rain. These systems are carefully monitored and tracked, and their presence is noted in the log. A strong depression can deliver several days of continuous rain across a wide area, significantly boosting seasonal totals. The Arabian Sea plays a similar role for the western branch of the monsoon, feeding moisture to the west coast of India and occasionally spawning cyclonic systems that enhance rainfall. In Africa, Lake Victoria and other large lakes can modify local monsoon patterns. The lakes act as local moisture sources and can enhance convection in their vicinity. In North America, the Gulf of California provides moisture for the North American monsoon, and the Sea of Cortez helps sustain the flow of humid air into the southwestern deserts. These bodies of water are logged as contributing factors in the moisture budget, small but important entries in the overall accounting. The role of soil moisture in the monsoon is another subtle but important factor. When the monsoon arrives and rain begins to fall, the land surface is initially dry, especially after months of dry season. The first rains are absorbed quickly, recharging soil moisture and groundwater. As the season progresses and the soil becomes saturated, more of the rainfall runs off into streams and rivers rather than soaking in. But the presence of moist soil also feeds back into the atmosphere. Evaporation from wet soil adds moisture to the air near the surface, making it easier for convection to develop. This feedback can enhance subsequent rainfall events. Conversely, if a break period allows the soil to dry out significantly, it can make it harder for convection to restart when the active phase returns. The attendance log tracks not just rainfall, but also soil moisture levels, river flows and reservoir storage, recognizing that the land surface is an active participant in the monsoon system, not just a passive recipient of rain. Vegetation also plays a role. Forests and croplands transpire water into the atmosphere, adding moisture to the boundary layer. During the monsoon season, when vegetation is green and growing, transpiration rates are high, contributing to the local moisture budget. Some studies suggest that deforestation and changes in land use can weaken local monsoon circulations by reducing this moisture recycling. The attendance sheet might include notes on land cover, forest cover stable, transpiration contributing as expected, or in regions experiencing rapid land use change, deforestation observed, possible reduction in moisture recycling. These are small adjustments, but over time they can influence the character of the monsoon in a given area. Urban areas introduce their own modifications to monsoon patterns. Cities are heat islands, with temperatures often several degrees warmer than surrounding rural areas due to heat-absorbing pavement, buildings, and reduced vegetation. This urban heating can enhance convection, sometimes triggering or intensifying thunderstorms downwind of the city. The urban heat island effect gets logged as a local factor influencing storm frequency and intensity. On the other hand, urbanization can reduce infiltration and increase runoff, leading to rapid flooding during heavy rain events. The monsoon delivers the same amount of rain, but the urban landscape responds differently than natural terrain. The attendance sheet includes entries for urban versus rural responses, noting how the same atmospheric pattern produces different outcomes depending on the surface below. The monsoon's influence extends to ocean processes as well. During the monsoon season, strong winds over the ocean can drive coastal upwelling, bringing cold, nutrient-rich water to the surface. This upwelling supports marine productivity and fisheries. In the Arabian Sea, monsoon winds drive upwelling along the coast of Oman and Somalia, creating one of the most productive marine ecosystems in the world. The timing and strength of the monsoon directly affect the timing and intensity of this upwelling. Fishermen track the monsoon not just for the rain it brings on land, but for the changes it brings to the ocean. The attendance log expands to include ocean conditions, sea surface temperatures, upwelling indices, and fishery productivity, all linked to the monsoon cycle. The historical record of monsoons stretches back centuries, far beyond the era of modern instruments. Paleoclimate researchers study monsoon variations using proxy data. Tree rings, lake sediments, cave formations, ice cores, and ancient written records. These proxies reveal that monsoons have varied over long timescales, responding to changes in Earth's orbit, ice sheet extent, and greenhouse gas concentrations. During the mid-Holocene, several thousand years ago, monsoons were generally stronger in many regions due to changes in Earth's orbital parameters that enhanced summer heating in the northern hemisphere. Written records from China, India, and Egypt document monsoon failures and floods over the past few millennia, providing a cultural memory of variability. The attendance sheet, in its long-term form, is not just a product of the modern era. It's a continuation of record-keeping that humans have engaged in for as long as they've depended on seasonal rains. The format has changed, from inscriptions on stone to handwritten ledgers to digital databases, but the fundamental purpose remains: to track the arrival, performance, and departure of the rains. Modern forecasting of monsoon behaviour is a major scientific and operational challenge. Seasonal forecasts attempt to predict whether a monsoon season will be above normal, near normal, or below normal in terms of total rainfall. These forecasts are issued weeks or months in advance, based on statistical models, dynamical climate models, and an understanding of factors like El Niño and sea surface temperature patterns. The accuracy of these forecasts has improved over the decades, but uncertainties remain. Monsoon systems are complex, with many interacting components, and small changes in initial conditions can lead to different outcomes. Forecasters present their predictions probabilistically. 60% chance of above normal rainfall, for example, acknowledging the inherent uncertainty. The attendance sheet in this context becomes a tool for verification. After the season ends, the forecast is compared to what actually happened, and the results are logged. Over time, this feedback loop helps improve the models and methods. Within a monsoon season, shorter-range forecasts predict day-to-day and week-to-week variations. When active and break phases will occur, where heavy rainfall is expected, when and where flooding might be a concern. These forecasts rely on weather models, satellite data, and real-time observations. They're updated daily, providing guidance for farmers, water managers, disaster response teams, and the general public. The attendance log feeds into these forecasts and is updated by them, creating a continuous cycle of observation, prediction, verification, and adjustment. The monsoon also interacts with human-induced climate change in ways that are still being understood. While the basic physics of land-sea heating contrasts won't disappear, the magnitude and character of monsoons may shift. Some modelling studies suggest that global warming could intensify monsoon rainfall in some regions because a warmer atmosphere holds more moisture. Other studies suggest that changes in aerosol pollution, tiny particles in the atmosphere from industrial activity and biomass burning, could affect monsoon strength by altering the amount of sunlight reaching the surface and changing cloud properties. Aerosols can either enhance or suppress rainfall depending on their type and concentration, adding another layer of complexity. The attendance log in the 21st century is not just a record of natural variability, it's also a record of how human activities are reshaping the atmosphere and, potentially, the monsoon itself. Adaptation to monsoon variability is an ancient practice, but it continues to evolve. Traditional water harvesting systems like tanks and stepwells in India were designed to capture and store monsoon rain for use during the dry season. Modern infrastructure, dams, reservoirs, irrigation networks, serves a similar purpose on a larger scale. Agricultural practices have been adapted to the monsoon calendar, sowing dates timed to coincide with expected onset, crop varieties selected for their ability to thrive with monsoon rainfall, and diversification strategies to manage risk. Urban planning is increasingly considering monsoon impacts, with efforts to improve drainage, reduce flood risk, and manage stormwater sustainably. The attendance sheet informs all of these efforts, providing the data needed to design infrastructure, plan planting schedules, and manage water resources. The monsoon's cultural significance is profound. In many regions, the arrival of the monsoon is celebrated with festivals, songs, and rituals. It's a time of renewal, relief from the heat, and hope for a good harvest. Literature, music, and art have long been inspired by the monsoon. Ancient Sanskrit poetry describes the onset of the rains with vivid imagery. Indian classical music has specific ragas associated with the monsoon season. Monsoon festivals in South Asia mark the end of the dry, hot pre-monsoon period and the beginning of cooler, greener conditions. The monsoon is not just a meteorological phenomenon, it's woven into the fabric of culture and identity. The attendance sheet in this light is not merely a scientific record, but a chronicle of a deeply human relationship with the rhythms of the atmosphere. There are also ecological dimensions to the monsoon. Many ecosystems are adapted to the seasonal pulse of moisture. Deciduous forests shed their leaves during the dry season and burst into new growth when the monsoon arrives. Grasslands green up and support grazing animals. Wetlands fill and become habitats for migratory birds. The timing of plant flowering, insect emergence, and animal breeding is often synchronized with the monsoon. Disruptions to the monsoon, late onset, early withdrawal, weak rains, can ripple through these ecological systems, affecting food webs and biodiversity. The attendance log, in ecological applications, is used to study phenology, the timing of natural events and how they correlate with climate patterns. The monsoon also shapes river systems and sediment transport. During the monsoon season, rivers swell with runoff from heavy rains. Sediment eroded from hillsides and agricultural fields is carried downstream, sometimes building deltas and floodplains, sometimes causing problems with reservoir sedimentation. The annual flood pulse in rivers like the Ganges, the Brahmaputra, the Mekong, and the Niger is driven by the monsoon. These floods are natural events that have historically supported agriculture by depositing nutrient-rich sediments on floodplains. Modern river management often tries to control or dampen these floods, but the monsoon's influence remains fundamental. Hydrologists track river discharge alongside monsoon rainfall, logging flow rates, sediment loads, and flood extents as part of the large monsoon record. Monsoons can also trigger natural hazards. Intense rainfall can cause flash floods, landslides, and debris flows, especially in mountainous terrain. The same orographic lift that produces record rainfall totals can also create dangerous conditions on steep slopes. Soil becomes saturated, slopes become unstable, and gravity takes over. In densely populated regions, these hazards can lead to loss of life and property. Disaster management systems monitor monsoon conditions closely, issuing warnings and coordinating response efforts. The attendance log becomes a tool for hazard assessment, identifying high-risk periods, tracking rainfall intensity, and comparing current conditions to historical thresholds. At the same time, the monsoon is a source of life and prosperity. It fills aquifers, replenishes lakes, and supports ecosystems. It enables agriculture in regions that would otherwise be too dry to farm. It cools the air and provides relief from extreme heat. The dual nature of the monsoon, both hazard and blessing, is reflected in the way societies engage with it. The attendance sheet records both the benefits and the risks, logging rainfall totals alongside flood damages, crop yields alongside landslides. The goal is not to eliminate the monsoon or control it, but to understand it well enough to maximize benefits and minimize harm. The scientific understanding of monsoons continues to deepen. New satellite instruments provide ever more detailed views of atmospheric moisture, cloud properties, and rainfall rates. Advances in computing power allow for higher resolution climate models that can simulate monsoons with greater fidelity. Field campaigns deploy instruments across monsoon regions to collect data on winds, temperature, humidity, and aerosols, filling in gaps in the observational record. International collaborations bring together researchers from multiple countries to study monsoons as global phenomena with regional expressions. Each new data set, each new model run, each new analysis adds another entry to the attendance log, refining our understanding of how monsoons work and how they might change. The monsoon is a testament to the interconnectedness of Earth's systems. It links the ocean to the land, the tropics to the subtropics, the surface to the upper atmosphere. It connects weather to climate, short-term variability to long-term patterns. It ties together physical processes, ecological systems, and human societies. The attendance sheet, in its simplest form, is a list of dates and numbers. But behind those numbers is a story of energy, moisture, motion, and change. A story that repeats every year but is never exactly the same twice. As the night deepens and the rhythm of your breathing slows, you can imagine that quiet office in the sky still at work. The logs are being updated even now. Somewhere a monsoon is in full swing, clouds towering, rain falling, rivers rising. Somewhere else, a monsoon is withdrawing, winds shifting, skies clearing, the dry season returning. The attendance sheet is always open, always recording. The monsoon clocks in, does its work, and clocks out, as faithful as the Earth's rotation, as predictable as the seasons, as essential as the sun. The pattern continues, reliable and patient, waiting for the next cycle to begin. The next story is about to begin. Please relax and enjoy. The ocean rests tonight, as it has for millions of nights before, a deep layer of water settling over a seafloor that moves so slowly you could never see it happen. If you were to open the operations log for this particular stretch of the Pacific, you would find entry after entry of the most ordinary measurements: tide levels, water temperatures, the gentle rise and fall that comes twice daily as the moon pulls and releases. Nothing in these numbers suggests drama. They are the quiet accounting of a stable system, a resting ocean doing what resting oceans do. But beneath that calm surface, beneath kilometers of dark water, the solid Earth is doing something patient and relentless. It is storing energy. The seafloor is not one smooth piece. It is a patchwork of enormous slabs called tectonic plates, each one sliding past or beneath or away from its neighbours at speeds measured in centimetres per year. Imagine running your hand along a table and moving it forward by the width of your fingernail over the course of 12 months. That is the pace. For most of the year, for most of a century even, the ocean above notices nothing. The water simply follows gravity, forming a level surface on top of this gradually shifting base. The operations log records no disturbance. The waves that pass through are wind waves, surface chop, the ordinary traffic of weather systems moving across thousands of kilometers of open water. Below, the plates continue their slow work. There are places where one plate meets another in a particular way, where one slab of oceanic crust slides beneath a neighbouring plate in a process that happens along a boundary stretching for hundreds or thousands of kilometres. These boundaries are called subduction zones, and they are among the most geologically active features on the planet, though you would never know it from the surface. At a subduction zone, the descending plate does not slide smoothly. Friction locks the two plates together along their interface, even as the deeper portions of the descending slab continue to sink into the mantle below. This creates a problem. The plate wants to move, but the locked zone refuses to let it. Stress accumulates. The upper plate is dragged downward slightly, bent and compressed like a board held under tension. Years pass, decades, sometimes centuries. The ocean above remains level, the logbook remains boring, and the stress continues to build. Then, on an afternoon or a morning, or in the middle of the night when no one is watching, the locked section fails. The friction that has held the plates together for so long gives way, and the upper plate snaps back toward its original shape. The release is sudden, but the motion itself is not violent in the cinematic sense. A segment of the seafloor, perhaps 100 kilometers long and 50 kilometers wide, shifts upward by 2 meters, or 3, or 5. Another section nearby may drop by a similar amount. The earthquake that results from this motion is powerful, shaking the ocean floor and sending seismic waves through the crust. But the water above does not immediately respond to the shaking. Water is not rigid. It does not transmit seismic shear waves the way rock does. What the water responds to is the change in shape of the basin beneath it. When a section of seafloor rises, the water column directly above it is displaced upward. When a section drops, the water above it must fill the new void. In both cases, the ocean's surface is no longer level. There is now a broad, shallow hill of water over the uplifted region, and a broad, shallow depression over the subsided region. These features are not steep. They do not look like the breaking waves you see at the beach. Spread out over tens or hundreds of kilometers, the surface gradient is so gentle that if you were floating in a boat directly above the source, you might not notice the change at all. But gravity notices. Gravity does not tolerate an uneven surface. The ocean begins to adjust, and in doing so, it sets a wave in motion. This is the first entry in the tsunami logbook. Source event recorded, seafloor displacement estimated, initial water column adjustment in progress. The wave that has just been born does not resemble the mental image most people have of a tsunami. It is not a towering wall of water. It is a very long, very low rise in sea level that begins to propagate outward from the source region in all directions. The wavelength of this disturbance can be 100 kilometers or more from crest to crest, and in the deep ocean, where the water may be 4 or 5 kilometers deep, the wave height might be only 30 or 40 centimeters. If you were standing on the deck of a ship as this wave passed beneath you, you would experience a slow, gentle lifting and lowering over the course of several minutes, so gradual that you might attribute it to ordinary swell. But this wave is not ordinary. It is a shallow water wave, a term that sounds contradictory when you are sitting above an ocean basin several kilometers deep. But in the language of fluid dynamics, a wave is classified as a shallow water wave when its wavelength is much larger than the water depth. For such waves, the speed of propagation depends almost entirely on the depth of the water, not on the height or period of the wave itself. The formula that governs this relationship is simple and appears in the logbook without fanfare. The speed equals the square root of gravitational acceleration multiplied by water depth. In the deep Pacific, where the average depth might be 4,000 meters, this gives a speed of around 700 kilometers per hour, roughly the cruising speed of a commercial airliner. The wave moves fast, but it moves quietly. As the wave spreads outward from the source, it carries energy. The energy was provided by the earthquake, by the sudden motion of the seafloor, and now it is distributed across the wavefront, travelling through the ocean in all directions. The wave does not break, it does not curl or foam, it simply propagates, a broad swell moving through the deep water, raising and lowering the surface by a few tens of centimeters as it goes. Ships pass over it without incident. Satellites can detect it if they are looking carefully, measuring the slight change in sea surface height using radar altimetry. But from the perspective of someone on the water, the ocean looks calm. The operations log records the wave's progress in terms of travel time. If the earthquake occurred at a known location and time, and if the depth of the ocean along various paths is known, then the arrival time of the wave at distant points can be calculated. The wave spreads as an expanding circle, or rather as an expanding set of arcs, because the ocean floor is not uniform. The speed of the wave changes as the depth changes, and the wave bends and refracts as it encounters ridges, trenches, and seamounts. Some energy travels directly across the basin. Some energy bounces off the edges of continents and reflects back into the ocean. Some energy is focused by underwater topography, concentrated along certain paths and diminished along others. The result is a complex pattern of wave arrivals, not a single crest but a train of waves, each separated by tens of minutes or hours, each contributing to the total signal. The bathymetry of the ocean floor acts as a quiet routing system. A wave travelling over a mid-ocean ridge will slow down slightly as the water becomes shallower, and then speed up again as it descends into the next basin. A wave approaching a deep trench will accelerate as it crosses into deeper water. Where the ocean floor has a gradual slope, the wave's path will curve, bending according to the changing depth in a process called refraction, similar to the way light bends when it passes from air into water. None of this is dramatic. It is geometry and physics, playing out over thousands of kilometers, and the logbook treats it as such. Wave refracted by emperor seamounts. Wave reflected off Aleutian margin. Secondary arrival expected due to basin resonance. Hours pass. The wave crosses the Pacific, moving from the subduction zone off Japan toward the coasts of North and South America, or from the coast of Chile toward Japan and the Philippines, depending on where the source was. In the open ocean, the wave remains small and fast, but as it approaches a coastline, the situation changes. The continental shelf is a region where the ocean floor rises gradually from the deep basin toward the shore, and as the wave moves into shallower water, it begins to slow down. The formula still holds. Speed depends on depth, so as depth decreases, speed decreases. But the wave's period, the time between successive crests, does not change. The energy carried by the wave does not disappear. With a slower speed and the same period, the wavelength shortens and the wave height increases. This process is called shoaling, and it's the reason why a wave that was barely noticeable in deep water becomes a significant threat near the coast. The transformation is gradual but inexorable. As the wave moves from water 4 kilometers deep to water 2 kilometers deep, it slows from 700 kilometers per hour to about 500. As it moves into water 1 kilometer deep, it slows to about 350. As it reaches the continental shelf, where the water may be only 100 or 200 meters deep, the speed drops further to around 100 to 150 kilometers per hour. And as the wave slows, it grows. A wave that was 30 centimeters high in the deep ocean might be a meter high on the outer shelf, 2 meters high as it approaches the inner shelf, and several meters high as it reaches the coast itself. The exact amplification depends on the shape of the seafloor, the slope of the shelf, and the configuration of bays and headlands, but the trend is clear. Energy that was spread over a long, low wave in deep water is compressed into a shorter, higher wave in shallow water. The operations log now shifts from propagation times to coastal impact estimates. The wave height at the shelf edge is calculated, the run-up potential is assessed, and the local bathymetry is consulted to determine which sections of coast are most vulnerable. A gently sloping shoreline will allow the wave to run inland over a considerable distance, flooding low-lying areas but dissipating energy gradually. A steep, rocky coast will see a more abrupt surge, with water rising rapidly against cliffs and seawalls. A funnel-shaped bay can amplify the wave height through a process called resonance, where the shape of the bay causes the water to slosh back and forth, reinforcing the incoming wave and producing water levels higher than would occur on an open coast. Each of these factors is noted, each produces a different entry in the log, and each determines the specific hazard at a specific location. It is important to note that the wave, even as it approaches the coast, is not a breaking wave in the usual sense. It is not like a surfing wave that curls and crashes onto the beach. It is more like a very rapid and very powerful tide, a sustained rise in sea level that continues for minutes or tens of minutes, pushing water inland and then, after the crest passes, pulling it back out to sea. The first motion may be a rise, or it may be a drawdown, depending on whether the initial seafloor displacement near the source was upward or downward, and on the exact path the wave travelled. If the first arrival is a trough rather than a crest, the water along the coast will recede dramatically, exposing the seafloor and stranding boats and fish before the first crest arrives and floods the area. Either way, the motion is sustained and forceful, more like a sudden change in tide level than a single breaking wave, and there is not just one wave. The initial disturbance of the seafloor generates a series of waves, and as these waves travel across the ocean, they are joined by reflected and refracted energy from other parts of the basin. The first wave may be the largest, or it may not. Sometimes the second or third wave in the sequence is the most destructive. The waves arrive over a period of hours, and in some harbours and bays the oscillations can continue for a day or more as the water sloshes back and forth, gradually losing energy to friction and turbulence. The operations log records each arrival, each oscillation, building a detailed timeline of the event as it unfolds. Not every tsunami is generated by an undersea earthquake. Submarine landslides can also displace large volumes of water very quickly, especially along steep continental slopes or in fjords and narrow bays. If a section of the seafloor or the coastline collapses and slides downward, it pushes water out of the way, creating waves that can be locally very large. These waves tend to be shorter in wavelength than earthquake-generated tsunamis, and they often affect a more limited area, but within that area, they can be just as destructive. Volcanic eruptions, particularly those that involve the collapse of a volcanic island or a large explosive event that displaces water, can also generate tsunamis. The 1883 eruption of Krakatoa, for example, produced waves that killed tens of thousands of people along the coasts of Java and Sumatra. Even the impact of a large meteorite into the ocean could theoretically generate a tsunami, though no such event has been recorded in human history. In each case, the logbook tags the event with a different source mechanism, but the basic physics is the same. A rapid vertical displacement of water leads to the generation of long-period waves that propagate outward and amplify as they approach shallow water. Detection of tsunamis begins with the source event. When a large earthquake occurs beneath the ocean, seismometers around the world record the seismic waves within minutes. Automated systems at tsunami warning centers analyze the data, determining the location, depth, and magnitude of the earthquake. If the earthquake is shallow and large, and if it occurs in a region known for tsunami generation, an initial alert is issued. This is the first line in the operational response log. Possible tsunami generated, preliminary assessment based on seismic data, warnings issued for at-risk coastlines. At this stage, the warning is precautionary. Not every large undersea earthquake produces a significant tsunami. Some earthquakes involve mostly horizontal motion, which does not displace much water. Others occur too deep below the seafloor to cause significant vertical displacement. The initial alert is based on statistical relationships and regional history, not on direct observation of the wave itself. Direct observation comes from a network of instruments specifically designed to detect tsunamis in the open ocean. These instruments consist of pressure sensors anchored to the seafloor, often in water several kilometers deep, connected by acoustic or cable links to surface buoys that relay the data to satellites. The pressure sensors are extremely sensitive, capable of detecting the change in water pressure caused by a sea level change of just a centimeter or two. When a tsunami passes over the sensor, the added weight of the elevated water column increases the pressure at the seafloor, and this change is recorded. The data are transmitted to the warning centers, where they are compared with the predictions from numerical models. If the observed wave height matches or exceeds the predictions, the warnings are confirmed and updated. If the observed wave is smaller than expected, the warnings may be downgraded. Each pressure measurement becomes a new entry in the logbook, a real-time update on the wave's actual behavior. Closer to shore, tide gauges provide another layer of observation. These instruments are installed in harbors, on piers, and along open coastlines, and they continuously measure the height of the water surface relative to a fixed reference point. Normally, they record the twice-daily rise and fall of the tides, along with smaller variations due to weather and ocean currents. When a tsunami arrives, the tide gauge records a deviation from the expected tidal curve. A sudden rise, a rapid drawdown, or a series of oscillations superimposed on the normal tide. The data are time-stamped to the second and archived in regional databases. After an event, these records are analysed to determine the exact arrival time, the maximum wave height, and the duration of the oscillations at each location. The logbook grows denser with each station's contribution, a detailed chronicle of how the wave interacted with each stretch of coast. Behind the scenes, forecast models are running. These models are sophisticated computer simulations that solve the equations of fluid dynamics on a grid that covers the entire ocean basin. They take as input the estimated seafloor displacement from the earthquake, the detailed bathymetry of the ocean floor, and any real-time observations from buoys and tide gauges. They calculate how the wave will propagate, how it will refract and reflect, and how it will shoal as it approaches the coast. The output is a set of predicted arrival times and wave heights for hundreds or thousands of coastal locations. Forecasters review these predictions, compare them with incoming data, and adjust the models as needed. The process is iterative and methodical, a continuous refinement of the event log as new information becomes available. The warnings issued by tsunami warning centers are formal and structured. They specify the regions under threat, the expected arrival times, and the estimated wave heights. They include information on whether the threat is local, regional, or ocean-wide. They provide guidance on evacuation and protective actions. As the event unfolds, updated bulletins are issued, incorporating new observations and refining the estimates. Each bulletin is a snapshot of the best available understanding at that moment, another line in the operations log that links physical measurements to human decisions. The tone is calm and factual, designed to convey urgency without panic, to provide the information needed for people to make informed choices about their safety. After the waves have passed and the water has settled, the scientific work continues. Survey teams travel to affected coastlines to document what actually happened. They measure high water marks on buildings and trees, they map the inland extent of flooding, they record debris lines and flow directions. These observations are compared with the predictions from the models, and the discrepancies are analysed. Was the run-up higher or lower than expected? Did the wave focus its energy in unexpected ways? What role did local topography and structures play in modifying the flow? The answers to these questions feed back into the models, improving their accuracy for future events. The logbook closes the loop, from the initial seismic detection of the earthquake, through the propagation of the wave across the ocean, to the final measurement of water levels on land. The entire sequence is documented, analysed, and archived. Most of the time, the ocean is quiet. Most of the time, the logbook records only the ordinary fluctuations: tides, storm surge, seasonal variations in sea level. The tectonic plates continue to move, the stress continues to build, but the locked boundaries remain locked. The seafloor does not shift. The water does not need to adjust. The long wave log returns to its baseline state, a series of unremarkable entries that stretch forward day after day, year after year. The instruments continue to monitor, the models continue to run in test mode, the warning systems remain on standby, the ocean rests, but the potential is always there. Beneath the calm surface, the plates are inching along. Friction is holding them in place, but friction is not infinite. Somewhere along a subduction zone, the stress is approaching the threshold where the rocks will fail. It could happen tomorrow, or it could happen in a century, but eventually it will happen. The seafloor will shift, the water will respond, and a new sequence of entries will appear in the logbook. The wave will be generated, it will propagate, it will amplify, and it will be detected. The warnings will be issued, the models will be run, the observations will be recorded. The process is well understood now, documented in countless technical papers and operational manuals, encoded in algorithms and databases. The operations log treats tsunamis not as unpredictable monsters, but as long, carefully documented waves, generated by well-understood physical processes, tracked by networks of instruments, modelled by sophisticated software, and measured at every stage from source to shore. There is a certain comfort in this perspective, in the quiet, methodical accounting of cause and effect. A tsunami is not magic. It is not the wrath of the gods or the inexplicable fury of nature. It is a predictable consequence of the way our planet works, of the way tectonic plates move and the way water responds to changes in the shape of its container. It is a phenomenon that can be observed, measured, modelled, and understood. The logbook is thick with data, each entry a small piece of the larger picture, each measurement a contribution to our collective knowledge of how these waves behave. The wave's journey from source to shore is a study in the transformation of energy. At the moment of the earthquake, the energy released by the sudden motion of the seafloor is enormous, but it is distributed over a vast area. As the wave propagates across the ocean, that energy is carried along, spreading outward in all directions, but also being shaped and redirected by the geometry of the ocean floor. Some energy is lost to friction and turbulence, but most of it continues to travel, patient and relentless, until it encounters the resistance of shallow water and the obstruction of the coast. There, the energy that was spread over a long, low wave is compressed into a shorter, higher wave, and the water's potential to do work, to move objects and erode land, increases dramatically. The transformation is predictable, quantifiable, and the logbook traces it from start to finish. In the decades since the first modern tsunami warning systems were established, the quality and quantity of data have improved enormously. The network of seismometers is denser and more sensitive. The deep ocean pressure sensors are more reliable and more widely distributed. The tide gauges are more precise and more numerous. The bathymetric data are more detailed, derived from satellite altimetry and ship-based sonar surveys that map the ocean floor with resolution measured in meters rather than kilometers. The computational models are more sophisticated, running on faster computers and incorporating more accurate representations of the physics. The result is a forecast system that can, within minutes of a large undersea earthquake, provide initial estimates of tsunami arrival times and wave heights for coastlines thousands of kilometers away, and then refine those estimates as real-time observations come in. The system is not perfect. Nature is complex and there are always surprises, but it is far better than what existed even a generation ago. The human element in all of this is significant but easy to overlook in the purely technical account. Behind every entry in the logbook there are people seismologists monitoring earthquake data, oceanographers analysing buoy readings, forecasters interpreting model output, emergency managers making decisions about evacuations, engineers designing resilient coastal infrastructure, educators teaching, communities about tsunami risk and response. The logbook is a technical document, but it serves a fundamentally human purpose, which is to reduce the harm caused by these waves. The goal is not to prevent tsunamis, that is impossible, but to provide enough warning, enough information, and enough understanding that people can take protective action and survive. There is also a historical dimension to the logbook. The written and oral histories of coastal communities contain many accounts of tsunamis, some dating back hundreds or even thousands of years. In places like Japan, where the risk is high and the historical memory is long, stone markers have been placed on hillsides to indicate the safe elevation above past tsunami run-up. In other regions, geological evidence preserves a record of ancient events: sand layers deposited far inland by tsunami inundation, subsidence features left by the sudden drop of the seafloor during an earthquake, coral blocks lifted above the normal tidal zone by the force of the waves. By combining these historical and geological records with modern instrumental data, scientists can build a more complete picture of how often large tsunamis occur, which regions are most at risk, and what the worst-case scenarios might look like. The logbook extends back into the past, informing our expectations for the future. The process of issuing and cancelling warnings is itself carefully documented. When an earthquake occurs, the initial bulletin is issued within minutes, based solely on seismic data. This bulletin may be quite general, warning of the potential for a tsunami without providing specific details. As the first deep ocean buoy data arrive, usually within an hour or two, the bulletin is updated with observed wave heights and refined arrival time estimates. If the observed wave is small, the warnings may be downgraded or cancelled for distant coastlines. If the wave is larger than expected, the warnings may be expanded or elevated. As the wave arrives at coastal tide gauges, the bulletins are updated again with observed local heights and the duration of the threat. The final all-clear message is issued only after the oscillations have diminished to safe levels and there is no longer a risk of dangerous currents or additional wave arrivals. Each of these steps is logged, creating a detailed timeline of the warning process that can be reviewed and critiqued after the event. In some cases, the source of a tsunami is ambiguous or difficult to characterize quickly. A large undersea landslide may not produce a strong seismic signal, making it hard to detect and locate using earthquake data alone. A volcanic eruption may involve multiple phases of collapse and explosion, complicating the assessment of how much water was displaced. In these situations, the first indication of a tsunami may come from coastal tide gauges or from reports from ships and coastal observers, rather than from seismometers or deep ocean buoys. The warning process must be flexible enough to respond to these less common scenarios, and the logbook must accommodate entries that do not follow the standard earthquake source template. The long-period nature of tsunamis also has implications for how they interact with harbours and bays. A harbour is, in a sense, a resonant cavity, a body of water with a particular geometry that can amplify certain frequencies of oscillation. If the period of the incoming tsunami waves happens to match the natural resonant period of the harbour, the water level inside the harbour can oscillate much more strongly than the open coast wave height would suggest. This is why some harbours experience severe damage and strong currents even when the offshore wave is relatively modest. The resonance can cause the water to slosh back and forth for many hours, long after the initial wave train has passed. Forecasters must take this into account, using models that simulate not just the propagation of the wave across the ocean, but also the detailed hydrodynamics inside bays and harbours. Another aspect of tsunami behaviour that appears in the logbook is the phenomenon of edge waves, which are waves that travel along the coastline rather than directly toward it. When a tsunami arrives at a coast, some of the energy is reflected back out to sea, but some of it is trapped along the shore and propagates parallel to the coastline. These edge waves can travel hundreds of kilometres along the coast, affecting regions that are not directly in the path of the initial wave. They can also interact with the incoming waves in complex ways, producing interference patterns that lead to higher or lower water levels at different locations. The logbook tracks these secondary effects, adding layers of detail to the overall event record. The concept of wave dispersion is generally less important for tsunamis than it is for shorter period waves, but it is not entirely negligible. Dispersion refers to the fact that waves of different wavelengths travel at different speeds, causing a wave packet to spread out over time. For tsunamis, which have very long wavelengths, the dispersion is weak, and the wave train tends to stay coherent over large distances. However, for very long propagation paths, such as a wave crossing the entire Pacific Ocean, there can be some spreading and separation of the different frequency components. This is typically a small effect, but it can be observed in the data and is included in the most detailed models. The energy budget of a tsunami is another topic that the logbook addresses, at least implicitly. The total energy generated by the earthquake is distributed among several processes. Some goes into seismic waves that travel through the crust, some goes into heat and deformation of the rocks near the fault, and some goes into the tsunami. The fraction that goes into the tsunami depends on the geometry of the fault rupture, the depth of the water, and the efficiency with which the vertical motion of the seafloor is transferred to the water column. Once the tsunami is generated, the energy is further distributed as the wave spreads, with some energy being absorbed by friction and turbulence, some being reflected back into the ocean, and some being dissipated as the wave runs up onto land and does work moving sediment, destroying structures, and flooding coastal areas. Tracking this energy flow from source to final dissipation is a complex problem, but it is central to understanding the overall impact of the event. There is also the question of how tsunamis are perceived and remembered by the people who experience them. The physical logbook is one kind of record, precise and quantitative, but the human experience of a tsunami is something else entirely. The sudden evacuation, the uncertainty, the relief when the warnings are cancelled, or the devastation when the waves arrive and prove to be as destructive as feared. These experiences shape community preparedness and influence how seriously future warnings are taken. A community that has experienced a false alarm may be less inclined to evacuate the next time. A community that has experienced a destructive event will carry that memory for generations and will likely be more responsive to warnings, more invested in mitigation measures, and more aware of the risk. The operations log does not capture these human dimensions directly, but they are an essential part of the larger story. From a purely observational standpoint, the modern era of tsunami science began in earnest after several large destructive events in the mid-20th century highlighted the need for better detection and warning systems. The 1960 Chilean earthquake, for example, generated a tsunami that caused damage not only along the Chilean coast, but also across the Pacific, killing people in Hawaii, Japan, and the Philippines. The travel times across the Pacific were on the order of a day or more, long enough that a warning system could, in principle, provide useful advance notice. The tragedy was that such a system did not yet exist in a fully operational form. In the decades since, the networks have been built, the models have been developed, and the procedures have been tested and refined. The logbook has grown thicker, and the understanding has deepened. As you imagine the ocean tonight, resting quietly under the stars, you can picture the instruments scattered across the seafloor and along the coasts, all of them recording, all of them waiting. The seismometers are listening for the faint rumble of an earthquake. The pressure sensors are measuring the weight of the water above them with exquisite precision. The tide gauges are tracking the slow rhythm of the tides. The satellites are orbiting overhead, their radar altimeters bouncing signals off the sea surface and measuring its height to within centimeters. All of this data flows into computers, where it is analysed, archived, and made available to scientists and forecasters around the world. The logbook is being written in real time, continuously, a living document that captures the state of the ocean and the solid earth beneath it. And somewhere, perhaps right now, a tectonic plate is inching forward, locked against its neighbour, building stress. The logbook notes the long-term motion, the gradual accumulation of strain, but it cannot predict the exact moment when the lock will fail. That moment will come as a surprise, at least in the immediate sense, though in the larger sense it is entirely expected. The plate will slip, the seafloor will shift, and the water will respond. A new wave will be born, broad and low, carrying energy across the basin, and the instruments will detect it, the models will simulate it, the forecasters will analyse it, and the warnings will be issued. The logbook will record every step: source, propagation, arrival, impact, aftermath. The ocean will eventually settle back into its resting state, and the logbook will return to its baseline entries, waiting for the next event. This is the nature of the ocean's long-wave log: patient, methodical, comprehensive. It does not judge or dramatize. It simply records what happens, when it happens, and how it happens, building a detailed technical archive of one of nature's most powerful and far-reaching phenomena. And in doing so, it transforms the tsunami from an inscrutable disaster into an understood process, something that can be anticipated, measured, and to some degree managed. The waves will continue to come, generated by the restless motion of the Earth's crust, but the logbook will be there to document them, line by line, entry by entry, turning raw observations into knowledge and knowledge into the possibility of protection. The next story is about to begin. Please relax and enjoy. Tonight's storm log is just filling out the form. There are no sirens in this version, no breaking news banners scrolling across screens, just the slow walkthrough of paperwork the atmosphere quietly completes on days when tornadoes are possible. A tornado isn't a sudden jump scare. It's the end of a long checklist, a series of ingredients and thresholds and tiny imbalances that sometimes line up. We're simply reviewing how a plain thunderstorm slowly qualifies for a higher level of organization, box by box, line by line, until the final entry can be made. A thunderstorm in its most basic form is an updraft machine. Warm, humid air near the surface rises because it's lighter than the cooler air above. As it climbs, it cools, and water vapor condenses into droplets that form towering clouds. These clouds grow vertically, sometimes reaching heights of 10 or 12 kilometers, their tops flattening against the stable layer of the stratosphere like a hand pressed against a ceiling. Raindrops form, grow heavy, and fall. The falling rain drags air downward, creating a downdraft. This basic convection, rising, cooling, sinking, is the starting point for everything else. It's the simplest circulation the atmosphere knows how to build. Most storms stop here. They check the lift box and the moisture box, rain themselves out in 20 or 30 minutes, and never approach tornado criteria. The file gets closed before the second page is even opened. Instability is the first critical ingredient, the fuel line on the checklist. Picture a thermometer column, hot at the ground, cooler higher up. When you have a warm, moist layer near the surface sitting beneath much cooler air aloft, you create buoyancy. A parcel of air, if lifted, stays warmer than its surroundings and keeps rising on its own, accelerating upward like a balloon released underwater. The larger this temperature and moisture contrast, the more energy is available for storms to tap into. Forecasters write down a number called CAPE, convective available potential energy, as a quiet numerical summary of how eager air is to rise. It's measured in joules per kilogram, and on severe weather days, values might climb into the thousands. High CAPE means the atmosphere is loaded with potential energy, ready to convert warmth into upward motion. But CAPE alone doesn't start anything. It's just fuel sitting in the tank, waiting for someone to turn the key. Moisture is its own line item, tracked separately. The simplest gauge is the dew point, the temperature to which air must be cooled for water vapor to condense. Higher dew points mean more water vapor in the air, and more water vapor means more latent heat release when condensation occurs inside a storm. That heat release is what powers the updraft, making it stronger and more persistent. On days with potential for severe weather, meteorologists track dew points creeping northward across the plains like a slow, damp boundary on the map. Values in the mid-60s Fahrenheit are noteworthy, 70s are impressive. In the paperwork metaphor, moisture is a separate row that must reach a certain threshold before the other ingredients matter much. You can have all the instability in the world, but if the air is too dry, storms struggle to organize or even initiate. Lift is the nudge, the gentle shove that gets air parcels rising in the first place. Cold fronts, warm fronts, dry lines, outflow boundaries, terrain. All of these features force surface air to move upward. The vertical velocities involved are often modest, just a few kilometers per hour. But when the environment is unstable, that's enough. A cold front acts like a wedge, sliding under warmer air and forcing it to rise. A dry line is a boundary between dry air and moist air, and along that invisible seam, the moisture contrast creates lift. Outflow boundaries are the leading edges of cold pools from earlier storms, and they can trigger new convection when they plow into unstable air. On the checklist, lift is a simple checkbox. Something needs to be pushing or nudging air upward. or the other ingredients sit unused. The atmosphere can be primed and ready, but without a trigger, nothing happens. The form stays blank. Wind shear is a quiet but crucial column in the tornado checklist. Shear means winds changing in speed or direction with height. Near the ground, you might have southerly winds at 10 miles per hour. A kilometre up, the winds might be southwesterly at 30 miles per hour. 2 kilometres higher, they might be westerly at 50. This vertical change in the wind creates horizontal tubes of weak rotation in the atmosphere. You don't feel them directly, they're just a pattern in the wind profile, invisible and abstract. Forecasters summarise this with numbers like bulk shear, measured in knots over a depth of the atmosphere, and storm relative helicity, which accounts for how the winds change relative to a moving storm. These numbers get written neatly in the margin of the storm file. Quiet metrics that mean everything when it comes to whether a thunderstorm will rotate. The magic happens when a strong, persistent updraft tilts those horizontal tubes of spin into the vertical. Imagine a pencil lying on a table. That's your horizontal vortex tube created by wind shear. Now imagine someone grabbing one end and lifting it upward. The pencil pivots, standing more and more upright. That's what the updraft does. As air rises, it pulls sections of the rotating tube upward, converting horizontal wind shear into a rotating column inside the storm. This vertical rotation is the core of a mesocyclone in a supercell thunderstorm. On the form, this is the point where storm-scale rotation gets circled. The regular thunderstorm has graduated. It's no longer just convection, it's a rotating storm, and that changes everything. Supercells are thunderstorms with a long-lived, rotating updraft. They separate their updraft and downdraft regions in space, allowing them to persist for hours instead of minutes. Inside a supercell, air rises strongly in one region, the updraft, while rain-cooled air descends elsewhere in the downdraft. This separation prevents the cold pool from immediately cutting off the storm's own fuel supply, a problem that kills ordinary storms quickly. The updraft keeps feeding on warm, moist inflow while the downdraft handles the storm's precipitation. It's an elegant division of labour. In the storm log, a supercell is a box with multiple sub-checklists. Strong updraft, check. Rotation, check. Separated downdraft, check. Organised structure, check. Each one is a small confirmation that the storm is operating at a higher level of complexity. The mesocyclone itself is a broad, rotating region within the mid-levels of the storm, typically a few kilometres above the ground. It's not a tornado. It's not even visible. It's rotation aloft, a large-scale invisible gear inside the storm's machinery. Forecasters track mesocyclones on radar by watching for velocity couplets, areas where inbound and outbound winds are adjacent, indicating rotation. The radar image shows greens and reds next to each other, winds moving toward and away from the radar site in a tight pair. This is the rotation column filled in part of the checklist. The storm has satisfied the rotation requirement. But rotation aloft doesn't guarantee anything at the surface. Many mesocyclones never produce tornadoes. They spin quietly in the mid-levels, never managing to lower that rotation to the ground. The checklist stalls here more often than not. Lowering the rotation requires another set of conditions. Strong inflow of warm, moist air into the storm's updraft region can help lower the base of the cloud, forming a wall cloud. A wall cloud is just a localized lowered portion of the storm's base where rising air is most focused. It's often rain-free, sometimes slowly rotating, and it hangs beneath the main cloud base like a shelf. Wall clouds are visual hints that the storm is reorganizing its inflow and maybe tightening its rotation. They're not tornadoes, but they're a sign that the storm is working on the problem. On the form, the lowered base box gets checked. The storm is making progress toward the final entry, but it's still not there. The interaction of downdrafts with the updraft is critical and delicate. The rear flank downdraft, or RFD, is a region of sinking air that wraps around the rotating updraft from the rear of the storm. It's often drier and somewhat cooler than the inflow, but not as cold as the forward flank downdraft, which is the main downdraft region with heavy rain and hail. The temperature, moisture content, and strength of the RFD all matter. If the RFD is too cold, it can stabilize the surface layer and kill tornado chances. If it's too weak, it can't help concentrate rotation. But if it's just right, cool enough to create a localized pressure drop but not so cold that it chokes off the updraft, it can wrap around the mesocyclone and help tighten rotation near the surface. This is a quiet mechanical detail in the tornado checklist, a line item that doesn't make headlines but determines outcomes. The storm zone downdrafts must cooperate with the inflow in a precise way, or the process stops. A tornado forms when rotation at the surface intensifies and contracts into a smaller, stronger vortex. It's the same angular momentum principle that makes an ice skater spin faster when pulling in their arms. As the rotating column of air stretches vertically and tightens horizontally, wind speeds increase dramatically. The vortex becomes visible when water vapor condenses in the low-pressure core or when dust and debris are lifted from the ground. Under the right balance of instability, shear, inflow, and downdraft characteristics, this happens. The storm finally checks the tornado present box after many other boxes were already quietly filled. It's the last line in a long form, the culmination of a process that started hours earlier, with temperature profiles and wind soundings. Meteorologists see these processes unfold on radar. Reflectivity shows the distribution of rain and hail, and a hook echo is a curved appendage on the southwestern side of a supercell, where precipitation wraps around the mesocyclone. The hook is a classic signature, shaped like a backwards question mark or a fishhook, and it indicates that the RFD is wrapping around the updraft. Velocity data, displayed in different colours, show inbound and outbound winds next to each other, forming a couplet. When the couplet is tight and strong, and when it appears at low levels near the surface, that's a strong indication of tornadic rotation. In the logbook, these are just coloured shapes and numbers: hook visible, couplet present, rotation strengthening, gate-to-gate shear increasing. Each signature is another line in the storm's file, another piece of evidence that the checklist is being completed. The difference between a tornado watch and a tornado warning is the difference between potential and actuality, between the top of the form and the final entry. A watch is issued when conditions are favourable for tornadoes across a region. The ingredients are in place: instability, moisture, lift, shear. Many checklist items have been satisfied, and storms that develop are likely to be severe, possibly tornadic. The watch covers a large area, often several counties or even states, and lasts for several hours. It's a general note at the top of the file: potential today, be aware, keep an eye on developing storms. A warning, on the other hand, is issued when a tornado is imminent or occurring based on radar signatures or spotter reports. It's tied to one specific storm and covers a much smaller area, usually the storm's predicted path over the next 30 to 60 minutes. It's a specific entry. This one has met the criteria, take action now. The warning is the confirmation that the checklist has been fully completed for this particular cell. Trained storm spotters and the public play a vital role in confirming what radars infer. Spotters report wall clouds, funnels, tornadoes on the ground, hail sizes, wind damage. These reports are time-stamped and added to the storm's record, helping meteorologists refine warnings and storm histories. Radar can see rotation, but it can't always see the tornado itself, especially if it's rain-wrapped or weak. Spotter logs are the handwritten margin notes that confirm or correct what the radar-only file suggests. They provide ground truth, the eyewitness verification that turns a radar signature into a documented event. Over time, these reports accumulate, creating a detailed history of each storm, when it produced a tornado, where, for how long, how strong. Warnings are issued as polygons that outline the area at risk based on the storm's current location and expected track. The polygon is drawn on a map stretching ahead of the storm along its forecast path, and residents in that area are advised to take shelter. The path of the mesocyclone and any associated tornado is traced across the landscape, then archived. Each event leaves behind a simple trail: start time, end time, path length, width, and intensity estimate on the enhanced Fujita scale. These records form a quiet database of tornadoes, used more for statistics and research than for drama. They're entries in a ledger, data points that help scientists understand patterns and improve forecasts. Climatologists compile long-term tornado records to create risk maps and seasonal summaries. They count how often certain regions see severe weather and what time of year ingredients most commonly align. These maps are like annual reports, showing more entries in some corridors, the traditional tornado alley regions of the Central Plains, and fewer in others. The patterns are driven by geography and climatology, where warm, moist air from the Gulf of Mexico frequently meets dry air from the desert southwest, where jet stream dynamics often create strong wind shear in spring, where terrain and local effects enhance lift. The maps don't predict individual tornadoes, but they document how often the atmospheric checklist is satisfied in different places. Some counties see the full checklist completed multiple times per decade. Others see it once in a lifetime, or never. Most thunderstorms, even strong ones, never produce tornadoes. The checklist is rarely fully complete. A storm might have instability but weak shear, so it never develops rotation. It might have good shear but limited moisture, so the updraft is too weak to tilt the wind shear effectively. It might have great instability and shear but poor organisation, with the downdraft undercutting the updraft before rotation can develop at the surface. It might have a mesocyclone aloft but an unfavourable RFD that stabilises the low levels. Each missing box is a reason. The final entry doesn't get made. This is reassuring in its way. The atmosphere often tries partial combinations of ingredients without reaching the last step. It fills out half the form, or 3/4, then the storm weakens or moves into a less favourable environment. The paperwork is incomplete, so the tornado doesn't happen. Only a subset of storms quietly fill in all the boxes needed for tornado formation. There's a certain calm in understanding tornadoes this way, as outcomes of documented processes rather than random acts of chaos. Each tornado has a file, a set of conditions that led to its formation, radar signatures that showed its development, spotter reports that confirmed its presence, and damage surveys that recorded its effects. The atmosphere doesn't conspire in secret. It leaves evidence at every step. Temperature profiles, wind soundings, satellite images, radar loops, surface observations, all of these are part of the record. Meteorologists read the file as it's being written, watching to see if the checklist will be completed. When it is, they issue warnings and document what happens. When it isn't, they note which ingredients were missing and move on to the next storm. Tonight, imagine the atmosphere as a vast office, processing weather forms around the clock. Most forms are routine: rain showers, weak thunderstorms, cloudy skies. A smaller number are flagged for review: thunderstorms with some organisation, enough instability to warrant attention. Fewer still reach the stage where severe weather is likely: hail, damaging winds, perhaps a tornado. And only a tiny fraction of those complete the full tornado checklist, satisfying every requirement, ticking every box until the final line can be filled in. The process is mechanical, impersonal, governed by physics and fluid dynamics. There's no malice in it, no intent, just air responding to temperature gradients, pressure differences, and the rotation of the Earth. As you drift towards sleep, picture a storm moving across the plains, its radar signature evolving slowly over the course of an hour. First, a cluster of cells, ordinary and disorganized. Then one cell strengthens, its updraft tapping into instability. A hook echo appears as precipitation wraps around a developing mesocyclone. The velocity couplet tightens. A wall cloud lowers beneath the cloud base. The rear flank downdraft curls around the updraft, and rotation at the surface begins to intensify. Spotters report a funnel, then a tornado on the ground. The warning is issued, the polygon drawn, residents take shelter. The tornado tracks across open fields, leaving a narrow scar in the earth, then weakens and dissipates as the storm encounters cooler air. The file is completed and archived. Start time, end time, path length, estimated winds. The storm moves on, and the atmosphere begins filling out the next form. There's something almost soothing about the routine nature of it all, the way each storm is just another case study in atmospheric dynamics. The ingredients are well understood, the processes are documented, the thresholds are known, forecasters don't guess. They read the data, check the values, compare conditions to past events, and issue outlooks, watches, and warnings based on probabilities and signatures. When a tornado forms, it's because the checklist was completed. When it doesn't, it's because something was missing. The atmosphere is filling out forms constantly, and most of them are incomplete. That's the default state. Tornadoes are the exceptions, the rare instances when everything lines up. Consider the storm now as it weakens, its fuel exhausted, its rotation dissipating. The mesocyclone aloft loses coherence, the wall cloud lifts back into the cloud base, the hook echo softens, the velocity couplet broadens and weakens. The storm becomes ordinary again, just another thunderstorm producing rain and occasional lightning, no longer organised or rotating. The checklist, which had been nearly complete, empties itself as conditions change. The inflow weakens, the shear decreases, the instability is consumed. The storm file is closed, marked as a supercell with brief rotation, no tornado produced. It joins the majority, the thousands of storms each year that approach tornado criteria, but never quite reach it. Even the tornadoes that do form are often brief and weak, touching down for a minute or two, crossing empty land, leaving little trace. The enhanced Fujita scale rates tornadoes from EF to EF5 based on damage, and the vast majority are EF or EF1, with winds below 110 miles per hour. They tip over trees, peel shingles, scatter lawn furniture. They're documented, mapped and catalogued, but they don't make national news. They're entries in the database, evidence that the checklist was completed but with modest intensity. The stronger tornadoes, EF3 and above, are rare, occurring only when every ingredient is not just present but maximized. Extreme instability, strong shear, powerful inflow, ideal storm structure. Those are the storms where every line on the form is filled in with bold, confident strokes. The climatology tells a story of probabilities and patterns. Spring is peak season in the Central Plains because that's when warm, moist air from the Gulf most reliably meets strong jet stream winds aloft. Late spring brings the highest frequency of significant tornadoes, the ones that track for miles and cause substantial damage. But tornadoes can occur in any month, in almost any location where thunderstorms develop. The checklist can be completed in December or October in the southeast or the Midwest. It's less common, but it's possible. The ingredients just need to align. The atmosphere doesn't observe a strict calendar. It processes forms year-round, and occasionally one gets completed out of season. There's a quiet beauty in the mechanics of it all, in the way rotation is generated, concentrated, and stretched into a vortex. The physics are elegant: conservation of angular momentum, the tilting of vorticity, the balance of forces in a spinning column of air. The equations that describe tornado formation are the same ones that describe water draining from a bathtub or a figure skater pulling in for a spin. The atmosphere is just a very large, very complex fluid, obeying the same rules. There's no mystery, only intricate detail. As the night deepens and your thoughts slow, imagine the storm files being sorted and stored, each one labelled with a date, time, location. Each one containing the measurements and observations that told the story of that particular storm. Some files are thick, full of warnings and damage reports and photographs of debris. Others are thin, just a notation that conditions were favourable, but nothing developed. Together, they form a library of atmospheric behaviour, a record of all the times the checklist was attempted and how far it progressed. Tornadoes, when they occur, are the result of many atmospheric details lining up over time: temperature structure, moisture, lift, shear, storm organisation. Meteorologists treat them less like sudden surprises and more like carefully documented outcomes of known ingredients. The surprise isn't that tornadoes form, it's that they don't form more often, given how many storms approach the necessary conditions. The atmosphere is constantly trying to complete the form, but it rarely succeeds. That's the reassuring part, the reason most severe weather events don't include tornadoes, the reason most thunderstorms simply rain and fade. The paperwork is heavy, the checklist is long, the atmosphere usually leaves boxes unchecked, and when all the boxes do get checked, when the full process runs from start to finish, the result is documented, analysed and archived. There are no surprises in the record, only confirmations of what the data suggested. The tornado was forecast as possible because the ingredients were present. It occurred because the storm managed to organise them correctly. It ended because the conditions changed. The file is closed, the form is complete, and the atmosphere moves on to the next task. Think now about the forecasters themselves, sitting in quiet rooms hours before any storms develop, studying the morning weather balloon data. They launch these balloons twice a day from stations scattered across the country, each one ascending through the atmosphere with instruments that measure temperature, humidity, pressure, and wind at various levels. The data streams back in real time, and within an hour, forecasters have a vertical profile of the atmosphere, a snapshot of the ingredients column by column. They plot these soundings on charts, looking for steep temperature lapses, high moisture content near the surface, and wind profiles that veer and strengthen with height. It's detective work. piecing together whether today's atmosphere will support severe storms, and if so, what kind. They look at surface maps showing fronts and boundaries, regions where different air masses meet and lift is enhanced. They examine water vapor satellite imagery, watching for dry air aloft that might cap the atmosphere, a warm layer that acts like a lid on a pot, preventing storms from developing until it's eroded or breached. They calculate derived parameters, lifted index, K-index, total totals, all shorthand ways of quantifying instability and moisture. They look at numerical model forecasts that simulate how the atmosphere will evolve over the next 6, 12, 24 hours. By mid-morning, they've drafted an outlook, a preliminary assessment of where severe weather might occur and what threats are most likely. It's all paperwork at this stage, forms and charts and calculations, the atmosphere's resume laid out for inspection. As the afternoon warms and storms begin to fire, the forecasters shift to monitoring mode. Radar images update every few minutes, showing the life cycle of each cell. Satellite images show cloud top temperatures, which hint at updraft strength. The colder the tops, the higher and stronger the updraft. Surface observations stream in from automated stations, showing temperature, dew point, wind speed and direction, pressure trends. Lightning detection networks plot each strike, mapping the electrical activity within storms. Forecasters juggle all these data streams, watching for storms that show signs of organization, that begin to check the boxes on the tornado list. When a storm starts to rotate, when the radar shows a velocity couplet strengthening and lowering, when the reflectivity shows a hook echo forming, that's when the forecaster's attention sharpens. They zoom in on the storm, examine its structure, estimate its motion, and decide whether to issue a warning. It's a decision made under time pressure, balancing the need to give people enough lead time with the desire to avoid false alarms. They draw the polygon on the map, select the counties or portions of counties at risk, compose the warning text, what threats are expected, when, where to take shelter, and issue it. The warning scrolls across weather radios, pushes to smartphones, appears on television. The paperwork has moved from analysis to action, from form filling to public safety. After the storm passes, after the warnings expire and the skies clear, there's still work to do. Damage survey teams go into the field to assess what happened. They look at the patterns of destruction, the direction trees fell, the way roofs were peeled, the scatter of debris. They interview residents, gather photographs, use GPS to map the path. From this ground truth, they assign an EF scale rating, determine the tornado's length and width, note the start and end times. This information goes into the Storm Events Database, a national archive maintained for research and planning. Every tornado, every severe thunderstorm, every flash flood and hail report, all documented, time-stamped, geo-referenced. It's the atmosphere's permanent record, decades of forms filled out and filed away. Researchers use this database to study trends. Are tornadoes becoming more or less frequent? Is the geography of tornado activity shifting? Are outbreaks, days with many tornadoes, becoming more common? They correlate tornado occurrence with large-scale climate patterns, El Niño, La Niña, the phase of the Madden-Julian oscillation. They investigate why some storms produce violent tornadoes while others with similar ingredients produce only brief, weak ones. They use computer models to simulate supercells, running thousands of virtual storms to test hypotheses about how changes in shear or instability affect tornado likelihood. All of this is an extension of the checklist metaphor, an effort to refine the form, to understand which boxes matter most and under what conditions. Education and preparedness are also part of the paperwork. Schools conduct tornado drills, teaching children to move to interior hallways or basement areas when a warning is issued. Communities install sirens, outdoor warning systems that wail when a tornado is imminent. Weather services distribute spotter training materials, helping volunteers learn to recognize wall clouds, rotation, and other storm features. Building codes in tornado-prone areas specify tie-downs and reinforced structures, engineering solutions to help homes withstand wind. Emergency management agencies maintain shelters and response plans, lists of resources and contacts for post-storm recovery. Each of these efforts is another form, another checklist designed to reduce harm. The technology has improved over the decades. Doppler radar, introduced in the 1990s, revolutionized tornado detection by allowing forecasters to see wind motion inside storms, not just precipitation. Dual polarization radar, added more recently, provides information about the shape and variety of hydrometeors, raindrops, hailstones, debris, helping to confirm when a tornado has lifted objects into the air. Phased array radar, still experimental, scans the atmosphere faster, updating every minute instead of every 5, giving forecasters more timely information. Numerical weather prediction models have grown more sophisticated, running on supercomputers and assimilating millions of observations to produce forecasts with increasing accuracy. Smartphone apps deliver warnings directly to users based on their GPS location, bypassing the need for television or radio. Each advance improves the checklist process, making it faster, more precise, more reliable. Yet uncertainty remains. Even with all this technology, with all the understanding accumulated over decades of research, tornado forecasting is probabilistic. A tornado watch means tornadoes are possible, not guaranteed. A radar signature indicating rotation doesn't always mean a tornado will touch down. Some storms rotate for hours without ever producing a tornado. Others produce multiple tornadoes in quick succession. The atmosphere is chaotic, sensitive to small variations that can't always be measured or predicted. The checklist captures the broad requirements, but it can't account for every subtle interaction, every local fluctuation in temperature or wind. There's always a margin of uncertainty, a range of possible outcomes. This uncertainty is itself a kind of comfort. It means the atmosphere retains some complexity beyond full prediction, some reminder that nature operates on scales from the molecular to the continental, and we're observing from somewhere in the middle. The forms we fill out are approximations, useful and often accurate, but not omniscient. The tornado that wasn't forecast, the storm that exceeded expectations, the quiet afternoon that stayed quiet despite ominous morning data. All of these are reminders that the checklist is a tool, not a script. The atmosphere will do what it does, following physical laws we understand, but with enough variability that each day is a fresh case. Consider the human experience of all this, the way people in tornado-prone regions carry an awareness of severe weather throughout the spring and early summer. They check the forecast each morning, noting whether it's a day to pay attention or a day to relax. They listen for the tone alert on their weather radio, the sharp beep that precedes a watch or warning. They've practiced their response, where to go, what to bring, how long to wait before emerging. Some have basements or storm shelters, underground rooms reinforced against wind and debris. Others make do with interior closets or bathrooms, the most sheltered spaces in their homes. There's a quiet preparedness, a cultural knowledge passed down, part of living in a place where the checklist occasionally gets completed. And most of the time, nothing happens. The storms develop but don't rotate. The watch is issued but no warnings follow. The shelf cloud looks ominous but produces only heavy rain. The checklist is attempted but remains incomplete. People go about their lives, the brief heightened awareness fading as the skies clear. The atmosphere has processed another form and moved on, the file closed without a tornado entry. This is the norm, the background rhythm. The exceptions, when everything aligns, are dramatic and memorable, but they're outnumbered by the quiet days, the almost days, the days when the paperwork was started but never finished. In the deepest part of the night, when sleep is pulling you under, imagine the archive of all these storm files stretching back decades. Imagine the rows of data, the maps marked with tornado tracks, the satellite loops saved and stored, the spotter reports typed and filed. Imagine the forecasters who worked those days, the decisions they made, the warnings they issued, the lives potentially saved by accurate information delivered in time. Imagine the researchers poring over old data, looking for patterns, refining the understanding of how the checklist works. Imagine the slow, steady accumulation of knowledge, each storm adding a small piece to the overall picture. The tornadoes themselves, when they occur, are brief. Most last only a few minutes. Even the long-track monsters that carve paths across multiple counties are finished within an hour. The atmosphere completes the form, files it, and returns to more ordinary weather. The sky clears, the temperature drops, the winds calm. By the next morning, the only evidence might be a line of debris, snapped trees, damaged buildings. The rotation that seemed so powerful, so intent, was just air responding to gradients and forces, a temporary organisation that dissolved as soon as the ingredients changed. The vortex tightened, spun, and dissipated. leaving behind only the record of its passing. There's a strange peace in this impermanence, in knowing that even the most violent tornado is a fleeting thing, a momentary configuration of wind and pressure. The atmosphere is always moving, always reorganizing, never holding the same pattern for long. The checklist is filled out, filed, and replaced by a new form. The storms march eastward, carried by the jet stream, and in their wake, the air settles, the humidity drops, the sun returns. The next weather system brings its own set of ingredients, its own potential, its own checklist to complete or leave unfinished. As your breathing slows and thoughts dissolve into sleep, let the storm files fade into background, the checklist stacked neatly, the forms mostly incomplete. Let the atmosphere continue its work, processing weather patterns with indifferent precision, occasionally producing rotation, rarely producing tornadoes. The paperwork will be there tomorrow, new data streaming in, new storms developing, new decisions to make. But tonight the forms are just forms, the storms are just storms, and the spinning air, when it happens at all, is just another line in a very long, very detailed log. Close the storm file for tonight. The spinning air, when it happens, is just the final line in a long document, the last box in a series of checks. Most nights the form stays incomplete. The ingredients don't quite align. The storm doesn't rotate, or the rotation stays aloft, or the downdraft undercuts the updraft before anything can develop at the surface. The checklist helps explain why tornadoes are both understandable and uncommon, why the atmosphere can be primed for severe weather but still not produce a tornado. It's a process, not surprise. And tonight, as you drift towards sleep, the storms are just filling out forms, one careful line at a time, rarely reaching the end. The sky above continues its patient work, and you, below, can rest in the knowledge that most forms are never completed, most checklists never fully checked, most storms never quite making it to that final entry. The next story is about to begin. Please relax and enjoy. Tonight we're checking the totals, not with urgency or alarm, but with the quiet attention you might give to an old set of accounts you've been meaning to review. The universe, as it turns out, has a balance sheet, a ledger of matter and antimatter that should have cancelled out perfectly in the beginning, leaving behind nothing but light. But the books don't quite balance. There's a tiny surplus, a small leftover amount that refused to annihilate, and that modest discrepancy became everything. Stars, planets, mountains, oceans, you. This isn't a story of dramatic explosions or cosmic battles. It's the slow unfolding of how a nearly perfect cancellation left behind just enough to build a universe worth looking at. Let's start with what matter and antimatter actually are, setting aside any theatrical language. Every particle you encounter in daily life has a mirror version. The electron, which orbits atoms and flows through wires, has an anti-electron called a positron. The proton, sitting in every atomic nucleus, has an antiproton. Neutrons have antineutrons. These antiparticles aren't exotic in principle. They have the same mass as their ordinary counterparts, but opposite electric charge where charge applies, and opposite values for certain other quantum properties. When a particle meets its corresponding antiparticle, they annihilate. The mass of both vanishes, converted into energy in the form of photons, particles of light. It's a clean transaction. Matter plus antimatter equals radiation, nothing left over. In the simplest version of the early universe, this symmetry would have been exact. As the Big Bang unfolded and the universe was unimaginably hot, particles and antiparticles would have been created in perfectly matched pairs. Energy, abundant and concentrated, could spontaneously turn into a particle and its antiparticle simultaneously. This process, called pair production, happened constantly. A high-energy photon could become an electron and a positron. The reverse happened just as easily. When an electron and positron collided, they'd annihilate back into photons. The universe was a roiling sea of creation and destruction, with matter and antimatter appearing and disappearing in equal measure. It was like a ledger where every entry on the left had a corresponding entry on the right, every credit matched by a debit, the totals always summing to zero. As long as conditions remained symmetric, as long as the laws of physics treated matter and antimatter identically, this balance would hold. The universe would cool over time, and eventually the temperature would drop below the threshold needed for pair production. At that point, the creation of new particles would stop. What remained would be the existing inventory of matter and antimatter, and those particles would continue to find each other and annihilate. If the counts were perfectly equal, annihilation would proceed until nearly everything was gone, leaving a universe filled with radiation and essentially no matter. No atoms, no chemistry, no galaxies. Just light, spreading and cooling through an empty cosmos. The balance sheet would close cleanly, all accounts settled, nothing owed or left over. But that's not what happened. Observations tell a different story, one with a subtle but crucial twist. The universe does contain matter, lots of it, relatively speaking. Stars burn with hydrogen nuclei, planets form from heavier elements, your body is made of atoms. All of that is matter, and essentially no antimatter. The antimatter is gone, annihilated long ago, but the matter remains. How much remains? The asymmetry is small, almost invisible in percentage terms, but decisive in outcome. For roughly every billion particle-antiparticle pairs produced in the early universe, there was approximately one extra matter particle with no antimatter partner. When the annihilations were complete, those billion pairs turned into photons and disappeared from the material ledger, but the single surplus particle stayed behind. Multiply that tiny fraction across the entire early universe, and you get all the protons, neutrons, and electrons that now populate galaxies. The cosmic balance sheet is off by about 1 part in a billion. That's the error term. That's us. To talk about this imbalance more precisely, physicists use a concept called baryon number. Baryons are the heavy particles built from quarks. Protons and neutrons are the most familiar examples. Baryon number is a simple counting scheme. Assign each baryon a value of +1, assign each antibaryon a value of -1, add them up. In most processes we observe, baryon number is conserved. When particles collide or decay, the total baryon number before and after the interaction stays the same. If you start with 2 protons, you end with a configuration that still has a net baryon number of 2, even if the specific particles change. This conservation law is like a rule in accounting. Certain totals can't be altered without authorization. But if the universe today has more baryons than antibaryons, if the net baryon number is positive, then something must have violated or bypassed that rule early on, gently tilting the count in favor of matter. In the late 1960s, a physicist named Andrei Sakharov outlined 3 broad conditions necessary for generating such an imbalance. These aren't rigid equations, but guiding principles, checkboxes that must all be ticked for the universe to depart from perfect symmetry. First, there must be processes that can change baryon number. If baryon number were absolutely conserved under all circumstances, you could never create a net surplus of baryons. Second, certain symmetries must be violated. Specifically, the universe must not treat matter and antimatter identically in all situations. There must be a preference, however slight, for reactions that favour matter over antimatter. Third, the universe must be out of equilibrium. If conditions were static and reactions could run forward and backward with equal ease, any imbalance created would be immediately undone by the reverse process. Only in a changing, evolving environment, one where the universe is cooling, expanding, and shifting through different regimes, can an imbalance be locked in before it has a chance to cancel out. These 3 conditions are Sakharov's recipe for cosmic asymmetry. Meet all 3, and you open the door to a universe with leftover matter. The second condition, the requirement for symmetry violation, leads directly to some of the more subtle aspects of particle physics. Symmetries are statements about what doesn't change when you transform a system. 2 symmetries are particularly relevant here: charge conjugation, denoted C, and parity, denoted P. Charge conjugation is the operation of swapping every particle in a system with its antiparticle. Parity is a spatial flip, like looking at the system in a mirror, reversing left and right. If the laws of physics were perfectly symmetric under C, then any process involving particles would have an identical counterpart involving antiparticles. If they were perfectly symmetric under P, then mirrored processes would behave identically. Often, physicists consider the combined operation CP, which swaps particles for antiparticles and flips spatial coordinates. If the universe respected CP symmetry completely, matter and antimatter would be indistinguishable except for their labels. There would be no way for the early universe to develop a preference for one over the other. The balance sheet would remain rigorously even, every entry mirrored perfectly. But CP symmetry is not perfect. It is broken, subtly and rarely, in certain particle interactions. The first hint came in the 1960s with experiments on particles called neutral kaons, which can oscillate between matter and antimatter versions. Researchers found small differences in how kaons and their antiparticles decayed. Later, more precise measurements with particles called bemesons confirmed similar effects. These CP-violating processes are not dramatic. The asymmetries are typically at the level of a fraction of a percent, appearing only in specific decay channels and requiring millions of events to detect statistically. But they are real, and they demonstrate that the laws governing particle interactions allow a slight bias. Matter and antimatter do not always mirror each other exactly. This opens the door, in principle, to an imbalance in the early universe. The second of Sakharov's conditions is satisfied by nature, at least to some degree. Particle accelerators around the world have spent decades cataloguing these asymmetries. By colliding particles at high energies and observing the resulting decays, physicists can measure how often a particular process occurs versus its CP conjugate counterpart. Over many collisions, patterns emerge. One decay might happen slightly more often for the matter version than for the antimatter version. Another might show a difference in the timing of decays. These differences are encoded in tables of measurements, each entry a small contribution to our understanding of how CP violation manifests. The experiments are like filling in rows of a detailed ledger, documenting the tiny preferences nature has for certain outcomes. It's meticulous, careful work, and it confirms that the ingredients for matter-antimatter asymmetry exist within the known laws of physics. However, there's a catch. The amount of CP violation observed in experiments with known particles appears insufficient to fully account for the matter surplus we see in the universe. The standard model of particle physics, which describes the electromagnetic weak and strong forces, does include CP violating terms, particularly in the weak force that governs certain radioactive decays. But when physicists calculate how much asymmetry those terms should produce in the early universe, the answer falls short of what's needed to explain the 1 part in a billion surplus of matter. This discrepancy suggests that additional sources of CP violation, not yet observed or understood, played a role. Perhaps new particles existed in the early universe that have since decayed away. Perhaps interactions beyond the standard model were important at those extreme energies. The balance sheet is partially reconciled. We know the sign, we see some contributions, but the full accounting remains under review. It's an open line item, a reminder that our current theories are incomplete. This brings us to the broader idea of baryogenesis, the general term for theoretical scenarios that explain how the universe generated its matter surplus. Different models propose different mechanisms, each a kind of procedural framework for how the early ledger might have been pushed off balance. Some models invoke the decay of heavy particles that existed only in the first moments after the Big Bang, particles that decayed asymmetrically into quarks and antiquarks. Others focus on processes associated with the electroweak force during a phase transition, a moment when the universe's properties shifted and symmetries were broken in new ways. Still others look to physics entirely beyond the standard model, proposing new fields or interactions that couple to ordinary matter in ways we haven't yet detected. Each model is a proposed narrative for how Sakharov's 3 conditions could have been met in practice, generating a small but decisive tilt toward matter. One particularly interesting class of models involves leptogenesis. Leptons are particles like electrons and neutrinos, distinct from baryons but related through the underlying structure of the standard model. Leptogenesis suggests that the universe first generated an asymmetry in leptons, rather than baryons directly. Perhaps heavy neutrino-like particles in the early universe decayed preferentially into neutrinos rather than antineutrinos. This creates a net lepton number, a surplus of leptons over antileptons. The standard model includes processes that can convert lepton number into baryon number under certain conditions, especially at the high energies present shortly after the Big Bang. Through these processes, the initial lepton asymmetry gets partially transferred into a baryon asymmetry. It's an indirect route, like shifting a balance in one column of the ledger and then using allowed accounting rules to move it to another column. The final result is more baryons than antibaryons, even though the initial asymmetry was generated in a different sector. This approach has the advantage of potentially explaining the matter surplus while also connecting to other puzzles, such as why neutrinos have mass and why that mass is so small. It's elegant in principle, though proving it happened requires understanding aspects of neutrino physics that remain unclear. Whatever the mechanism, the matter-antimatter asymmetry is not merely a theoretical conjecture. It's inferred from multiple lines of observational evidence, clues embedded in the universe's oldest light and in the composition of matter we see today. The cosmic microwave background, the faint glow of radiation left over from when the universe became transparent about 380,000 years after the Big Bang, carries information about the density of matter at that time. The relative abundances of light elements, hydrogen, helium, and trace amounts of lithium and deuterium, were set by nuclear reactions in the first few minutes, and those abundances depend sensitively on the ratio of baryons to photons. By fitting models to these observations, cosmologists can estimate the size of the matter surplus with surprising precision. The cosmic microwave background and primordial nucleosynthesis act like old receipts, documents that let us reconstruct the initial imbalance even though the events happened nearly 14 billion years ago. The numbers agree. The universe had a small but crucial excess of matter, about 1 extra baryon per billion photons, and that ratio shaped everything that followed. Today, the universe contains far more photons than baryons. The ratio is lopsided, with hundreds of millions of photons for every proton or neutron. This isn't a surprise given the annihilation story. Almost all the matter and antimatter in the early universe annihilated into radiation, swelling the photon count. What remains is a dilute gas of leftover baryons immersed in a vast sea of photons. Those photons have cooled over time as the universe expanded. They're now microwave wavelength photons, filling space with a nearly uniform glow at about 3 degrees above absolute zero. But their sheer number relative to matter particles is a direct record of the ancient annihilations. The balance sheet, viewed today, shows a large entry for radiation and a much smaller but absolutely critical entry for matter. Without that small matter entry, there would be nothing to form structures, nothing to collapse into galaxies and stars, nothing to eventually become us. It's worth pausing to appreciate just how small this asymmetry is and how large its consequences are. 1 part in a billion is a tiny fraction. If you lined up a billion particle-antiparticle pairs, only 1 extra matter particle would remain after annihilation. Yet that single particle, multiplied across the whole universe, accounts for every atom in existence. If the asymmetry had been zero, perfect symmetry maintained, the universe would be a cold bath of radiation with no complexity, no evolution, no life. If the asymmetry had been much larger, say 1 part in 1,000 instead of 1 part in a billion, the universe would have had far more matter early on, changing the dynamics of cosmic evolution, possibly affecting how galaxies formed and how stars burned. The actual value sits in a narrow range that allows the universe as we know it to unfold. It's a delicate numerical detail inserted at the very beginning, a slight tilt that everything else builds upon. What we consider normal, the presence of matter and structure, rests entirely on this early imbalance. Given that the universe has a matter surplus, one might wonder whether there could be regions dominated by antimatter instead, places where the tilt went the other way. Could there be entire galaxies made of antiprotons, antineutrons, and positrons? Observationally, this seems unlikely. If large antimatter regions existed, we'd expect to see characteristic signals at the boundaries where matter and antimatter domains meet. When matter and antimatter particles collide, they annihilate into high-energy photons, primarily gamma rays with specific energies. Astronomers have searched for such gamma-ray signatures on cosmological scales and haven't found compelling evidence. The lack of large-scale annihilation signals suggests the matter surplus was global, not patchy. The decision, so to speak, was made uniformly across the observable universe. Wherever we look, the same sign of asymmetry appears. This consistency hints that whatever process generated the imbalance operated coherently during a very early phase, before the universe had a chance to develop separate regions with different outcomes. The entire visible cosmos shares the same ledger error, the same tiny preference for matter that was locked in when conditions were still uniform and simple. It's also worth acknowledging the human side of this discovery, the fact that the matter-antimatter problem was recognized not through grand revelation, but through careful comparison of theory and observation. In the early 20th century, the existence of antimatter was predicted by Paul Dirac's equations, and the positron was discovered in cosmic rays in the 1930s. The idea that matter and antimatter should be created in pairs followed naturally from quantum field theory. But it was only as cosmology matured, as physicists began to model the hot early universe and calculate what it should produce, that the tension became clear. If everything was symmetric, there should be no matter left. Yet matter obviously exists. This gap between expectation and reality forced theorists to think harder about symmetry breaking, conservation laws, and the detailed processes occurring at extreme energies. Sakharov's conditions, proposed in 1967, framed the problem in a way that's still used today. The experimental detection of CP violation in the same era provided a concrete piece of the puzzle. Progress since then has been incremental. Better measurements, more refined models, deeper theoretical investigations. It's the steady accumulation of evidence and understanding, not a single dramatic breakthrough. The chain of consequences that flows from this tiny earlier symmetry is long and winding. The leftover protons and neutrons, cooled and thinned as the universe expanded, eventually clumped together under gravity. Small density fluctuations, seeded perhaps by quantum variations in the earliest moments, grew over time. Regions with slightly more matter pulled in more material, forming the cosmic web we see today. Vast filaments of galaxies separated by voids. Within those overdense regions, gas collapsed into the first stars. Stars fused hydrogen into helium and heavier elements, creating the chemical diversity that makes planets and life possible. When massive stars exhausted their fuel, they exploded as supernovae, scattering those elements into space to be incorporated into new stars and planets. Earth, its rocks and oceans, formed from such recycled material. The atoms in your body were forged in stars, and those stars existed only because the early universe had a small surplus of matter to work with. Every step from the formation of the first hydrogen nuclei minutes after the Big Bang to the assembly of complex molecules billions of years later depended on that initial imbalance. The universe's visible structure is an elaborated consequence of the fact that the cosmic ledger didn't quite balance. It's a long causal chain, but the starting point is a single, almost negligible asymmetry. There's something quietly profound in realizing that existence itself hinges on imperfection. If the universe had been perfectly symmetric, the story would have ended almost immediately. All particles would have annihilated, leaving behind only radiation, featureless and unchanging. Perfection, in this case, would have meant emptiness. Instead, the universe is slightly lopsided. The books are almost balanced, but not quite, and that not quite is everything. Mountains and oceans, forests and cities, thoughts and dreams, all of it traces back to a tiny discrepancy in the earliest moments. It's a reminder that what seems like an error, a deviation from the ideal, can be the seed of all complexity and richness. The universe we experience is built on a foundation of broken symmetry, a gentle departure from the most orderly outcome. Physicists continue to work on the details, searching for the full explanation. Experiments at particle accelerators probe CP violation with ever greater precision, hunting for new sources of asymmetry beyond what the standard model predicts. Cosmologists refine models of the early universe, exploring how different baryogenesis scenarios would leave imprints in the cosmic microwave background or the distribution of galaxies. Theorists propose new particles and forces, checking whether they could naturally produce the required asymmetry without conflicting with other observations. It's meticulous collaborative work, spanning decades and involving thousands of researchers. The goal is not just to confirm that the asymmetry exists, we already know it does, but to understand exactly how it arose, which processes were responsible, and what that tells us about the fundamental laws governing reality. Each new measurement, each refined calculation, is a line item added to the cosmic audit, bringing the balance sheet a little closer to full reconciliation. As you lie here tonight, the idea that you exist because of an accounting error might feel strange, almost arbitrary. But there's also something comforting in it. The universe didn't need to produce matter. It could have remained perfectly symmetric, a realm of pure light with no substance, no form. That it chose, in whatever sense the early universe chooses, to tilt slightly toward matter is the reason anything happens at all. Stars ignite, planets form, life emerges. The ordinary matter around you, the air you breathe, the ground beneath you, the distant stars, exists because the universe's ledger had a tiny surplus. It's an origin story without intentionality, without a grand designer adjusting the books. It's simply what happened when the laws of physics, with their subtle asymmetries and out-of-equilibrium conditions, played out in the extreme environment of the Big Bang. The result is a cosmos that contains both light and substance, both radiation and matter, and the matter, improbable and sparse as it is, builds everything we know. In the grand scheme, the matter-antimatter asymmetry is one piece of a larger puzzle about why the universe has the properties it does. Why is there something rather than nothing? Why does the universe have the constants and laws we observe? These questions may not have final answers, or the answers may involve aspects of physics we haven't yet discovered. But the matter surplus offers a more modest, tractable version of the question. Given that something exists, why is it matter rather than an equal mix of matter and antimatter? And for that question we have partial answers. We understand some of the necessary ingredients. We see evidence of CP violation. We can calculate, at least roughly, what kinds of processes could generate the observed asymmetry. We're filling in the ledger, line by line, checking the entries, reconciling the totals. The audit is far from complete, but the broad outlines are clear. It's easy, in daily life, to take matter for granted. The solidity of objects, the persistence of particles, the fact that atoms don't spontaneously annihilate. These seem like givens, background facts requiring no explanation. But they're contingent outcomes of specific conditions in the early universe. If the asymmetry had been different or absent, the universe would be radically unlike what we see. There would be no periodic table, no chemistry, no biological evolution. The story of how we got here is, in part, the story of how the universe avoided perfect symmetry. It's a story of small violations, subtle preferences, and a changing environment that locked in a slight imbalance before it could be erased. It's not a story of conflict or struggle, but of processes unfolding according to physical law, with outcomes that, viewed retrospectively, seem almost miraculous in their consequences. And so, as the night deepens and thoughts begin to drift, you can imagine the earliest moments of the universe as a vast, nearly balanced ledger. On one side, particles, on the other, antiparticles. Transactions occurring at unimaginable speed, pairs appearing and vanishing, the totals flickering but never settling. Then, as the universe cooled and expanded, the activity slowed. Pair production ceased. Annihilations continued until almost everything was gone, but not quite everything. A tiny fraction remained, unmatched, with no partner to cancel against. That fraction, 1 part in a billion, was left over. It drifted through the expanding cosmos, cooled into neutral atoms, clumped under gravity, formed stars and planets. Billions of years later, it became mountains and rivers, trees and animals, people looking up at the night sky and wondering why anything exists at all. The answer, as far as we can tell, is a subtle imbalance in the earliest transactions, a small error that refused to cancel out. The universe's books almost balanced, but not quite, and that not quite is everything. Close your eyes. The ledger error is still here, in every atom, a quiet reminder that perfection would have meant nothingness, and existence required a gentle deviation, a tiny tilt toward matter, preserved across billions of years. The audit continues, but for tonight, it's enough to know that the accounts, imperfect and beautiful, somehow added up to this, a universe with substance, with structure, with you. The next story is about to begin. Please relax and enjoy. Tonight is not about doomsday. It's about bookkeeping. Imagine the universe as a very large account, the kind maintained by a patient, methodical clerk who never takes a day off. Every process that occurs, every star that ignites, every ice cube that melts, every breath you take, adds a small, irreversible line to this ledger. The entries accumulate slowly, filling page after page, and they all point in the same direction. This direction is what we call entropy, and it tracks something simple: how spread out and unavailable energy becomes over time. Entropy is not a villain. It carries no moral weight, no emotional charge. It's just a number, a measure that tends to go up in isolated systems. Think of it as cosmic bookkeeping, a way of recording the universe's transactions. Each time energy moves from a concentrated form to a more dispersed one, The ledger records a small increase. The ice melts into water. The hot coffee cools to room temperature. The drop of dye spreads through the glass until the water is uniformly tinted. These are not dramatic events, but each one leaves a permanent mark in the account books. To understand what entropy actually measures, we need to think about the difference between what we see and what's really happening at the smallest scales. Consider a cup of coffee sitting on your desk. You observe a single thing. A cup of liquid at a certain temperature, maybe 70 degrees Celsius. That's the macrostate, the big picture description. But at the molecular level, there are countless ways to arrange the water molecules, caffeine molecules, and heat energy to produce that same observable cup of coffee. Each specific arrangement is a microstate. There might be trillions upon trillions of different microstates that all correspond to the same macrostate you're looking at. Now here's the key insight. There are usually many, many more microstates that look mixed up or spread out than ones that look organized or concentrated. If you have a container with hot water on one side and cold water on the other, there are relatively few microstates that maintain that sharp temperature difference. But there are vastly more microstates where the energy is evenly distributed and the temperature is uniform throughout. Over time, as molecules collide and exchange energy randomly, the system naturally drifts toward the macrostates that correspond to the most microstates, simply because those are the most probable destinations. The ledger entry, entropy increased, is just a shorthand way of saying the system moved into a state that could be realized in more ways. This is not a law that prevents any particular molecular motion. Water molecules don't know about entropy, they just bounce around according to the basic rules of physics. But when you have enormous numbers of them, say 10 to the power of 23 molecules in a glass of water, the statistics become overwhelming. It's not impossible for all the fast-moving molecules to spontaneously gather on one side of the glass and all the slow ones on the other, recreating a hot-cold divide. It's just so stupendously unlikely that you could wait longer than the age of the universe and never see it happen. The probabilities are so lopsided that the direction of change becomes, for all practical purposes, one way. Let's walk through some everyday examples to make this concrete. Take an ice cube from the freezer and drop it into a glass of warm water. The ice is a low entropy configuration in a certain sense. The water molecules are locked into a rigid crystal structure, and the thermal energy is concentrated in the liquid surrounding it. Over the next few minutes, heat flows from the warm water into the ice. The crystal structure breaks down, the water molecules in the ice gain kinetic energy and start moving freely, and eventually the entire system reaches a uniform temperature somewhere between the original temperature of the ice and the original temperature of the water. The energy that was localized in the warm water has spread out. The entropy of the combined system has increased. The ledger records this transaction. Energy dispersed, gradient flattened, entropy up. Or consider a hot cup of coffee left on the counter. The coffee starts out much warmer than the surrounding air. Heat flows from the cup into the room, carried away by air currents and infrared radiation. After an hour, the coffee has cooled to room temperature. The energy that was concentrated in the hot liquid is now distributed throughout a larger volume of air and has been radiated away as low-energy photons into the walls, the floor, the ceiling. The total energy is conserved. None of it vanished, but it's now spread out in a way that makes it much less useful for doing organized work. The coffee's high temperature was a gradient you could have harnessed in principle to run a tiny heat engine. Once the coffee and the room are at the same temperature, that opportunity is gone. The entropy of the room plus coffee system has increased. Another line in the ledger. One more, drop a single droplet of food colouring into a glass of still water. At first, you can see exactly where the dye is, a concentrated blob of colour. But even without stirring, the dye molecules begin to diffuse. They spread out, driven by random thermal motion. After a while, the entire glass is uniformly tinted. The dye molecules are now distributed evenly throughout the water. The macrostate, all the dye in one small region, corresponded to relatively few microstates. The macrostate dye evenly distributed corresponds to an astronomically larger number of microstates. The system moved from the less probable configuration to the more probable one. Entropy increased. The ledger notes it. These everyday processes all illustrate the second law of thermodynamics, which says that in an isolated system, entropy never decreases over time. It either stays the same if the system is already in equilibrium, or it increases. The law doesn't forbid energy from moving around, it just says that, on average, energy will spread out and gradients will flatten. The second law is statistical. It's not that every individual microstate has an arrow painted on it pointing forward in time. It's that the sheer number of high-entropy microstates is so much larger than the number of low-entropy ones that the direction of change becomes effectively irreversible. Now, why does this matter for doing useful work? Machines, engines, and even living organisms all rely on differences: temperature differences, pressure differences, chemical concentration differences, to drive organised processes. A car engine works because there's a difference between the hot, high-pressure gases produced by burning fuel and the cooler, lower-pressure environment of the exhaust. A hydroelectric dam works because there's a difference in height, and thus gravitational potential, between the water in the reservoir and the water downstream. Your body works because there's a chemical difference between the energy-rich molecules in food and the lower-energy waste products you excrete and exhale. In every case, when work is done, some of the input energy is inevitably converted into a lower quality, more spread out form, typically waste heat. No engine can be perfectly efficient. No process can convert all of the energy from a high-grade source into useful output without some loss. This is another way of stating the second law. You can't build a machine that continuously converts heat from a single reservoir into work without any other effect. Some energy always ends up increasing the entropy of the surroundings. In accounting terms, entropy is like a mandatory transaction fee. Every time you use energy to do something organized, you pay a small, unavoidable cost in the form of increased entropy somewhere. It's important to note the role of isolation here. The second law applies strictly to isolated systems that don't exchange energy or matter with their surroundings. Earth, for instance, is not an isolated system. It receives a steady stream of low-entropy energy from the sun in the form of visible light, and it radiates higher entropy energy back into space in the form of infrared radiation. This influx and outflow allows the Earth to maintain and even increase its internal order. Trees grow, animals evolve, civilizations build cities, all of which are decreases in local entropy. But this is only possible because the Earth is exporting entropy to the rest of the universe. When you account for the Sun, the Earth, and the surrounding space altogether, the total entropy is still increasing. The second law doesn't forbid local pockets of order, it just requires that the overall ledger, when you include everything, still trends upward. So much for ice cubes and coffee. Now let's zoom out to the largest scales and the longest timescales, the entire universe and its ultimate fate. To understand where the cosmic ledger is heading, we need to first understand where it started. The early universe, shortly after the Big Bang, was hot, dense, and remarkably uniform. Matter and radiation were distributed very evenly across space, with only the tiniest fluctuations, variations of about 1 part in 100,000. The radiation field was in thermal equilibrium, corresponding to a very high entropy state for the photons. But here's the twist. In terms of gravitational structure, the universe actually started in a surprisingly low entropy configuration. All that matter was spread out smoothly. It had not yet clumped into stars, galaxies, or black holes. There was enormous potential for structure formation, for gradients to develop, and for entropy to grow as gravity did its work. Think of it this way. If you have a box of gas, and you start with all the particles evenly distributed, that seems like a high entropy state. But if gravity is important, if the particles attract each other, then the situation is different. For a self-gravitating system, the smooth, uniform state is actually unstable and represents relatively low entropy. The particles can increase the system's entropy by clumping together, forming dense structures, releasing energy in the process. This is counterintuitive, but it's a crucial feature of how gravity works. As the universe expanded and cooled, those tiny initial fluctuations in density grew under the influence of gravity. Slightly denser regions attracted more matter, becoming denser still. Over millions of years, the smooth distribution of matter began to develop structure. Filaments, clusters, and eventually galaxies. Inside those galaxies, gas clouds collapsed further, heating up as gravitational potential energy was converted into thermal energy. When the cores of these collapsing clouds reached high enough temperatures and densities, nuclear fusion ignited and stars were born. Each of these processes, collapse, heating, radiation, increased entropy. When a gas cloud collapses under gravity, it doesn't just get denser, it also gets hotter. That heat is then radiated away into the surrounding space as infrared and visible light. The energy that was stored as gravitational potential energy in a diffuse cloud is converted into kinetic energy of the gas particles, heat, and then into radiation that spreads out into the cosmos. The radiation carries entropy away from the collapsing region, and the total entropy of the universe increases. The cosmic ledger records the transaction. Gravitational binding released energy. Structure formed, entropy rose. Stars themselves are magnificent. Long-lived engines that burn down gradients. A star like the Sun has a hot core where nuclear fusion converts hydrogen into helium, releasing energy. That energy works its way outward through the star, eventually radiating from the surface into the cold surrounding space. The temperature difference between the star's core, millions of degrees, and the surrounding interstellar medium, a few degrees above absolute zero, is an enormous gradient. The star is essentially a heat engine that slowly transforms low-entropy nuclear fuel into higher-entropy radiation. Over billions of years, the Sun will fuse most of the hydrogen in its core into helium. Eventually, it will exhaust its fuel, swell into a red giant, shed its outer layers, and settle down as a white dwarf, a dense hot ember that will cool over trillions of years. Every photon the Sun emits is a small step in this process. The concentrated energy stored in atomic nuclei is gradually converted into diffuse light and heat spreading out across space. The ledger notes each transaction: fuel consumed, light emitted, entropy increased. And the Sun is just one star among hundreds of billions in our galaxy, and there are hundreds of billions of galaxies in the observable universe. Each star is doing the same thing, converting low-entropy fuel into higher-entropy radiation. Across the cosmos, trillions of stars are contributing their entries to the ledger, day after day, year after year, eon after eon. On even larger scales, processes like star formation, supernova explosions, and the growth of supermassive black holes all contribute to increasing entropy. When a massive star exhausts its fuel, it can explode as a supernova, scattering heavy elements into space and releasing an enormous burst of energy. That energy heats surrounding gas, drives shock waves, and eventually radiates away into the cosmos. A supernova is a dramatic event, but in thermodynamic terms it's another entry in the ledger. Concentrated energy dispersed, gradients flattened, entropy up. Supermassive black holes lurking at the centers of most galaxies also play a role. As matter spirals into a black hole, it heats up and emits intense radiation, sometimes outshining the entire galaxy. This radiation carries away energy and entropy, further dispersing the energy that was once locked in the gravitational potential of the infalling matter. The accretion process is violent and energetic, but it's also a steady contributor to the universe's growing entropy account. Now, black holes themselves introduce a fascinating twist to the ledger. It turns out that black holes have entropy, a lot of it. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This means that a black hole represents an extraordinarily large number of microstates, even though from the outside it appears to be described by just a few parameters: mass, charge, and spin. When matter falls into a black hole, the entropy of the universe doesn't just stay the same, it increases significantly. The black hole is like a vast repository in the cosmic ledger, a compact object that carries an enormous entropy entry. A black hole with the mass of our Sun has an entropy of about 10 to the power of 54 in natural units. A supermassive black hole with 1 billion solar masses has an entropy roughly 10 to the power of 72. These numbers dwarf the entropy of ordinary matter. To put it in perspective, the entropy of all the stars, gas and planets in a galaxy is negligible compared to the entropy of the supermassive black hole at its center. Black holes dominate the entropy budget of the universe. They are the major contributors to the ledger's running total. Meanwhile, the universe as a whole continues to expand. As space stretches, light gets redshifted, its wavelength increases, its energy decreases. The cosmic microwave background, the afterglow of the Big Bang, started out as high-energy radiation filling the early universe. Over billions of years, expansion has stretched those photons into the microwave range. Today, the cosmic microwave background has a temperature of about 3 degrees above absolute zero. In the far future, it will cool even further, redshifting into radio waves and beyond. This expansion and cooling is another way in which energy becomes more diluted and less available for doing work. High-energy photons can drive processes. Low-energy photons are much less useful. The expansion of the universe acts like a slow backdrop to all the other processes, a gradual spreading of energy across an ever larger volume. The ledger records this too. Energy diluted, temperature dropped, entropy increased. For now, the universe is still in a vibrant, active phase. Stars continue to form, galaxies continue to collide and merge, black holes continue to grow. But the rate of star formation has been declining for billions of years. Much of the universe's initial supply of hydrogen and helium has already been processed through stars. Some of it is locked up in long-lived low-mass stars that will burn for trillions of years. Some has been converted into heavier elements, locked in planets and stellar remnants. Some has been heated to such high temperatures that it no longer easily condenses into new stars. As time goes on, the raw materials for star formation become scarcer. Galaxies run out of cold gas. The rate at which new stars are born drops. Fewer and fewer new engines are started. The universe will continue to have stars in active regions for a very long time, many trillions of years. But each generation leaves less fuel in forms that are easy to use. The ledger shows a declining rate of new, low-entropy structures being created. The universe is not winding down suddenly. It's doing so very, very gradually. Eventually, star formation will cease almost entirely. The universe will enter an era dominated by stellar remnants. White dwarfs, neutron stars, and black holes. White dwarfs are dense, Earth-sized embers, the cooling cores of dead stars. Neutron stars are even denser, the collapsed remnants of massive stars that exploded as supernovae. Black holes are the endpoints for the most massive objects. These remnants will continue to radiate energy, but at ever lower rates and temperatures. A white dwarf, for example, starts out hot, tens of thousands of degrees, but it has no internal energy source. It simply cools by radiating its heat into space. Over trillions of years, white dwarfs will cool to the temperature of the surrounding universe, eventually becoming black dwarfs, cold, dark, inert lumps of matter. Neutron stars follow a similar trajectory, cooling from millions of degrees to near absolute zero. The fireworks of star formation and the bright glow of galaxies give way to a universe of dim, slowly fading embers. Entropy continues to rise as heat flows from these remnants into the surrounding space, flattening temperature differences bit by bit. Even black holes are not permanent. Quantum effects near the event horizon allow black holes to emit radiation, a process discovered by Stephen Hawking in the 1970s. This Hawking radiation is incredibly faint for large black holes. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate, far, far longer than the current age of the universe. A supermassive black hole would take even longer, perhaps 10 to the power of 100 years or more. But given enough time, even the largest black holes will evaporate. As they do, their enormous entropy is gradually converted into a sea of very low-energy photons and particles. The ledger's largest individual entries are, in effect, dissolved into a smoother, more uniform background. The black hole radiates away its mass energy, bit by bit, until nothing is left but a faint glow of radiation spreading out into the vastness of space. What does the universe look like in this far, far future? It is almost unimaginably large, cold, and dilute. Most matter has either decayed, been absorbed into black holes that have since evaporated, or been converted into low-energy radiation. The distance between any two remaining particles is enormous. Interactions are rare. Temperature differences are tiny, approaching zero. There is still activity in principle. Particles still move, photons still propagate. But there is very little free energy available to drive organized processes. In accounting terms, almost all the available gradients have been drawn down. The energy that once powered stars, drove galactic dynamics, and supported the evolution of complex structures is now so evenly distributed that not much more can happen. The universe has reached a state of near maximum entropy, sometimes poetically called heat death. It's not that everything is literally hot. In fact, everything is very, very cold. The term heat death simply means that the energy has been so thoroughly spread out that it can no longer sustain the kind of flows and gradients that make interesting processes possible. This is the endpoint the ledger has been recording, entry by entry, for billions upon billions of years. It's not a catastrophe in any immediate sense. It's just the logical conclusion of the second law of thermodynamics applied to a closed system. In this case, the universe as a whole. Every process that increases entropy, from the melting of an ice cube to the evaporation of a black hole, is a step along this path. But here's something worth noticing. The direction of this process gives time its arrow. We experience time as having a direction, past, present, future, and that direction is intimately tied to the increase of entropy. We remember the past but not the future. We see glasses break but never spontaneously reassemble. We watch ice cubes melt, never freeze out of warm water on their own. Why? The answer is that the past had lower entropy than the present. The early universe was in a low entropy state, with matter spread smoothly and enormous potential for structure formation. As time went on, entropy increased. The processes we observe, melting, mixing, aging, forgetting, are all manifestations of this increase. Our memories themselves are low entropy structures, patterns encoded in neurons that require energy gradients to form and maintain. We remember the past because the past was a time when those gradients existed and could support the creation of records. We can't remember the future because the future hasn't happened yet, and also because the act of remembering requires accessing a low entropy record created by a past event. Breaking a glass is easy. It's easy because there are vastly more microstates corresponding to broken glass than to intact glass. The broken pieces can be arranged in countless ways, different positions, orientations, fragment sizes, and they all count as broken. There's essentially only one microstate, or a very small set, corresponding to the intact glass sitting on the table. When you drop the glass, it shatters, and the system moves from a low entropy configuration to a high entropy one. Reversing this, having all the fragments spontaneously leap up, fit together perfectly, and seal themselves into a smooth, unbroken glass, is not forbidden by the fundamental laws of physics. It's just so stupendously improbable that it will never happen. The arrow of time, the felt asymmetry between past and future, is rooted in this statistical behavior. Does this mean that life, complexity, and order are violations of the second law? Not at all. Life and other complex structures are not exceptions to the rule. They are local patterns sustained by exporting entropy to their surroundings. Earth is a wonderful example. The sun bathes the Earth in a steady stream of low entropy, high energy photons. Plants capture that energy through photosynthesis, building complex molecules and structures. Animals eat plants or other animals using the stored chemical energy to maintain their bodies, move, think, and reproduce. All of these processes require energy flows. But the Earth doesn't just absorb energy. It also radiates energy back into space. The key is that the outgoing radiation is at a lower temperature, longer wavelengths, and higher entropy than the incoming sunlight. The Earth receives low entropy energy and returns high entropy energy. The difference allows the biosphere, the atmosphere, the oceans, and the intricate systems of weather and climate to maintain and evolve complex order. The local decrease in entropy on Earth is more than compensated by the increase in entropy of the Sun and the surrounding space. The global ledger still shows an upward trend. These pockets of order, ecosystems, cities, individual organisms, are like small, temporary sub-accounts within the larger book. They exist because there are still strong gradients to tap. The Sun is much hotter than the Earth, and the Earth is much warmer than the cold of space. These differences drive flows of energy that can be harnessed to do work, to build structures, to sustain life. But as the universe ages and those gradients diminish, maintaining such pockets of order becomes harder. A universe in which stars have all burned out, black holes have evaporated, and energy is uniformly spread thin offers no gradients to exploit. The ledger still exists, but there are no more interesting transactions to record. It's worth pausing to appreciate the timescales involved here. The current age of the universe is about 14 billion years. The sun will continue to shine for another 5 billion years or so. The longest-lived stars, the small red dwarfs, will burn for trillions of years. White dwarfs will cool over timescales of 10 to the power of 15 years or more. Black hole evaporation takes place over timescales of 10 to the power of 60 to 100 years, depending on the mass. The approach to heat death is not a sudden event. It's an almost unimaginably slow fade that stretches across timescales that make the current age of the universe look like the blink of an eye. For all practical purposes, we live in an era rich with gradients and complexity. Stars shine, planets orbit, life evolves, civilizations rise. The cosmic ledger is still filling in its early pages, still recording active, interesting processes. There is no immediate cause for concern, no need to worry that the universe is about to run down tomorrow or in a million years or even in a trillion years. The slow drift toward higher entropy is a feature of the deepest laws of physics, but it plays out over timescales that are, for human purposes, effectively infinite. And yet there's something oddly comforting about this long view. The increase of entropy is not a malicious force or a design flaw. It's simply a reflection of how energy moves and redistributes itself when there are many, many particles involved. The second law of thermodynamics is not a prohibition. It's a statistical tendency, an accounting rule that describes the most likely direction of change. It allows for complexity, for structure, for life, as long as there are gradients to drive those processes. It even allows for local decreases in entropy, as long as the overall balance sheet tips upward. Think of the universe as that patient accountant, sitting at a vast desk, updating a ledger that stretches across billions of years. Each entry is small, a photon emitted, a molecule colliding, a star converting a bit more hydrogen into helium. The accountant doesn't hurry. There is no deadline, no rush. The work continues, entry after entry, page after page. Time's arrow is marked not by catastrophe, but by the gentle, ongoing spreading out of energy, from concentrated sources to diffuse backgrounds, from high-grade fuel to low-grade waste heat, from sharp gradients to smooth uniformity. The ledger itself is a curious object when you think about it. It has no physical form, no leather binding, no paper pages yellowing with age. It exists as a concept, a way of organizing our understanding of how the universe changes. Yet in another sense, it's the most real thing there is. Every atom, every photon, every quantum fluctuation is a participant in this grand accounting. The ledger is written in the language of thermodynamics, a language that describes not individual particles, but the collective behavior of inconceivably large ensembles. Consider what it means that the ledger is irreversible. When you add an entry, when entropy increases, you cannot erase it. You cannot undo the melting of the ice cube by simply reversing every molecular motion. In principle, the microscopic laws of physics are time reversible. If you could somehow reverse the velocity of every particle in a system, the process would run backward. The shattered glass would reassemble, the melted ice would refreeze, the mixed dye would unmix. But this requires an impossibly precise intervention, a godlike ability to control and manipulate every particle simultaneously. In practice, for any real system with more than a handful of particles, such reversal is beyond impossible. The irreversibility of the ledger entries is not because the fundamental laws forbid backward motion, it's because the starting conditions for backward motion are so extraordinarily specific and unlikely that they simply never occur naturally. Imagine trying to reassemble a shattered glass by throwing the pieces into the air with exactly the right velocities and spins so they collide, fuse, and form a perfect whole. The odds are not merely bad, they are so vanishingly small that the entire history of the universe, repeated countless times, would not be enough to see it happen even once. The ledger moves forward because forward is where the overwhelming majority of possible futures lie. This has profound implications for how we understand causality and time itself. In our everyday experience, causes precede effects. You drop the glass, then it breaks. You light the match, then the candle ignites. This temporal ordering feels fundamental, but it's actually a consequence of entropy. In a universe where entropy decreased instead of increased, the temporal ordering would appear reversed from our perspective. Events would seem to have effects that preceded their causes, but of course, inhabitants of such a universe would experience things as perfectly normal, with their own arrow of time pointing in the direction of their entropy increase. The arrow of time is not an external feature imposed on the universe, it emerges from the statistical behavior of matter and energy. One of the more subtle aspects of the ledger is that different systems can have different rates of entropy increase. A hot object in cold surroundings will have its entropy increase rapidly as heat flows out. A system already near equilibrium will have very slow entropy increase, with only small fluctuations occurring. The universe as a whole has a certain average rate of entropy production, but this rate changes over cosmic time. In the early universe, when matter was clumping and stars were forming at high rates, entropy was increasing rapidly. In the far future, when most processes have run their course and the universe is cold and dilute, the rate of entropy increase will be much slower, though it will continue as long as any gradients remain. This varying pace of change means that the ledger doesn't fill up at a constant rate. Some epochs see many entries added quickly, others see a slow trickle of small adjustments. Right now, in the current epoch, we're in a moderately active period. Star formation is declining from its peak billions of years ago, but it's still happening, galaxies are still merging, black holes are still growing. The cosmic ledger is being filled at a steady pace, neither frantically nor languidly. One of the questions that sometimes troubles people when they first encounter these ideas is whether the eventual heat death makes everything meaningless. If the universe is ultimately heading toward a cold, dark, featureless state, does that render our current existence pointless? This is more a philosophical question than a scientific one, but it's worth addressing briefly. The heat death of the universe is so remote in time, so many orders of magnitude beyond our normal experience, that it bears no relationship to the meaning or value we find in our daily lives. The fact that a sandcastle will eventually be washed away by the tide doesn't make building it meaningless in the moment. The fact that a symphony ends doesn't negate the beauty of the music while it plays. Moreover, meaning and purpose are not properties written into the fundamental laws of physics. They are emergent features of complex systems like human consciousness, things that arise in particular contexts with particular structures. The universe doesn't care whether entropy increases or decreases, it simply follows its statistical tendencies. But within the universe, in the brief epochs and small regions where gradients exist and complexity can flourish, beings like us can create, experience, and value things. The second law of thermodynamics doesn't comment on any of that, it just describes how energy spreads out. In fact, one might argue that the temporary nature of order makes it more precious, not less. If structures lasted forever, if gradients never ran down, there would be no change, no evolution, no history. The fact that stars burn through their fuel and eventually die is what allows them to shine brightly while they live. The fact that organisms must continually work to maintain their organization, eating, breathing, repairing damage, is what makes them active participants in the world rather than static objects. The flow of entropy through a system is what enables life, thought, and action. The ledger also reveals something interesting about information. Information and entropy are closely related concepts, though the relationship can be counterintuitive. In a sense, information is negative entropy. It represents structure, pattern, and order. When you erase information, you necessarily increase entropy. This is not just a metaphor, it's a physical fact. A computer's hard drive storing data is in a lower entropy state than the same drive with the data scrambled randomly. Erasing the data requires dissipating energy as heat, which increases the entropy of the surroundings. This connection between information and entropy means that the cosmic ledger is also, in a way, tracking the loss of information. As the universe evolves toward higher entropy, detailed information about past states becomes harder to recover. The specific microstate of the early universe, the exact position and momentum of every particle, is information that has been effectively scrambled and dispersed by subsequent evolution. You can't look at the current state of the universe and work backward to determine exactly how things were arranged 14 billion years ago, except in broad statistical terms. The information has been, in a sense, erased into the growing entropy. This is related to why we can't remember the future. Memories are information structures, low entropy patterns that encode details about past events. They exist because there were gradients available to create them. The future, by contrast, has not yet created such structures. When it does, when the future becomes the present and then the past, it will leave behind its own information traces, its own memory records. But from our current vantage point, looking forward, there are no such records to access. The asymmetry of memory is another manifestation of the arrow of time another way the ledger's one-directional filling makes itself felt in our experience. The gradual dissipation of information as entropy increases also has implications for what the far future universe knows about its own past. In a state of maximum entropy, where energy is uniformly distributed and no gradients remain, there are no structures that encode historical information. The universe in heat death, if such a state is ever fully reached, would be in a sense amnesiac, unable to maintain records of its earlier, more structured epochs. This isn't a conscious forgetting, of course. It's simply that the physical basis for storing information, differences, structures, patterns, would no longer exist. But we are nowhere near that state, and won't be for incomprehensibly long times. The universe currently has abundant structure, abundant information, abundant memory. Rocks record geological history in their layers. Light carries information about distant stars and galaxies. DNA preserves information about evolutionary history. Human brains store memories. Culture stores knowledge, and civilization builds libraries and databases. All of these are temporary, local, low-entropy structures sustained by the flow of energy through the biosphere, maintained by the sun's steady output of low-entropy photons. The cosmic ledger permits these pockets of information to exist, as long as the gradients that support them remain. There's also a subtle point about what we mean by the universe when we talk about its entropy. We usually mean the observable universe, the region of space from which light has had time to reach us since the Big Bang. But the universe might be much larger than the observable portion, perhaps even infinite. If it's infinite, then the total entropy is also infinite, both now and at any other time. What matters for the second law is not the absolute value of entropy, but its rate of change. An infinite universe can still have entropy increasing everywhere, with the cosmic ledger growing without bound, even though it started and will remain infinite. Furthermore, we don't know with certainty what happens in the very, very far future. Our current understanding is based on extrapolating known physics forward, but there could be phenomena we don't yet understand that become important on extremely long timescales. Perhaps there are slow processes involving the decay of matter itself. Protons might be unstable, though if so, they have lifetimes vastly longer than the current age of the universe. Perhaps the vacuum of space itself is not in its lowest energy state, and over immense times it could undergo a transition that changes the fundamental properties of physics. Perhaps quantum fluctuations in a near-empty universe could spontaneously create new structures, though such events would be so rare as to be essentially irrelevant. These speculations don't change the basic picture of the ledger steadily filling with entropy entries, but they remind us that our knowledge has limits. The second law of thermodynamics, as we understand it, is one of the most solid and well-tested principles in all of physics. It has never been observed to be violated in any isolated system. But our understanding of the universe's ultimate fate involves extrapolating over timescales that dwarf anything we can test or observe directly. A degree of humility is appropriate. Still, within the framework of what we do know, the picture is clear. The ledger records the spreading of energy, the flattening of gradients, the movement from improbable, low-entropy states to probable, high-entropy ones. This is not a process that happens quickly or dramatically. It's a slow, steady statistical drift that plays out over scales that make geological time look instantaneous. The universe is patient. The ledger has room for countless entries. There is no rush, no urgency, no impending deadline. As you settle in for the night, imagine that accountant at work. Imagine the ledger growing slowly and steadily as stars burn, ice cubes melt, and black holes evaporate over timescales that dwarf comprehension. The universe is not collapsing into chaos. It's not falling apart. It's simply redistributing its energy, balancing its books, and moving from one macrostate to another in the most probable way possible. The process is peaceful, even beautiful in its inevitability. Entropy is not the enemy. It's just a number, a tally, a quiet record of how things change. And for now, in this era of stars and galaxies and planets teeming with life, the ledger still has plenty of room left to record the transactions of an active, vibrant cosmos. The arrow of time points steadily forward, but that forward direction is not toward doom. It's simply toward a different kind of balance, a state where energy is shared more evenly and gradients have gently, gradually flattened out. So rest easy. The universe's ledger is in good hands. The bookkeeping is meticulous, the entries are irreversible, but that's just how the accounting works. Time's arrow is steady, pointing from past to future, from order to greater probability, from concentration to diffusion, and in the meantime, there are stars shining, planets turning, and countless small moments of organised complexity playing out across the cosmos. The ledger records them all, one line at a time, with the patience of eternity, never rushed, never anxious, simply documenting the quiet, inexorable flow of energy from here to there, from then to now, from what was concentrated to what becomes shared in a story written not in triumph or tragedy, but in the calm, steady arithmetic of thermodynamic law. The next story is about to begin, please relax and enjoy. Tonight we're not dealing with explosions or catastrophic collisions, we're simply reviewing the maps, the quiet, methodical blueprints that explain how the universe arranged its galaxies across billions of light years. On the largest scales, galaxies are not scattered randomly like sand grains on a beach. Instead, they line up along elongated structures called filaments, gather in dense clusters at intersections, and spread across broad walls, all while leaving enormous empty regions called voids. Cosmologists call this arrangement the cosmic web, and it's exactly what it sounds like. A sprawling three-dimensional network that resembles a vast spider's web stretching across space. Think of it as the universe's zoning plan, survey marks, infrastructure maps, and development documents that show where matter ended up and why. The story begins long before any galaxies existed, back when the universe was almost perfectly smooth. Almost, but not quite. In those earliest moments, tiny differences in density existed. Variations so small, they amounted to only a few parts in 100,000. These weren't dramatic features. They were subtle ripples in the hot plasma that filled space, barely distinguishable from the background. But they were there, and they mattered. Today we can see these ripples as faint temperature variations in the cosmic microwave background, that ancient light that has travelled across the universe for nearly 14 billion years. These temperature differences are like the first surveyor's marks on a blank plot of land. Faint pencil lines indicating where the foundations would eventually be poured. They didn't look like much, but they told gravity where to begin its slow work. Gravity is patient, it doesn't rush. These tiny density fluctuations gave gravity something to work with, regions where matter was ever so slightly more concentrated than the surrounding space. Over time, these slightly denser patches would attract more matter, while slightly less dense regions would lose material. The ripples acted as seeds, quiet instructions embedded in the fabric of space that would eventually determine where galaxies would cluster and where they would be scarce. The universe had its initial survey complete, its first set of marks placed. Now the real construction could begin, though it would take hundreds of millions of years before anyone could see progress. Most of the universe's matter, however, is not the ordinary stuff we're familiar with. It's dark matter, material that doesn't emit, absorb, or reflect light, making it invisible to telescopes. But dark matter does interact through gravity, and that's all gravity needs. While the early universe was still filled with hot plasma too energized for atoms to form, dark matter was already beginning to respond to those initial density ripples. It started to clump, slowly at first, forming concentrations in regions where the original fluctuations had been slightly more pronounced. These concentrations acted like invisible wells or depressions in the expanding universe, gravitational pits that would grow deeper over time. Think of dark matter as invisible scaffolding, the hidden framework behind the visible universe. While ordinary matter was still too hot and energetic to settle down, dark matter was already laying foundations. These dark matter halos, as astronomers call them, were the first structures to form. They weren't galaxies yet, just regions of space where dark matter had accumulated in slightly higher densities, creating gravitational wells that would later trap gas and dust. Nothing flashy was happening, nothing you could see even if you had been there with a telescope. Just gravitational depressions forming in the darkness, building plots marked out on the cosmic landscape where future neighbourhoods would eventually rise. Eventually, the universe cooled enough for ordinary matter, primarily hydrogen and helium gas, to respond to gravity's pull. This gas began to fall into the dark matter halos, following the paths that invisible scaffolding had laid out. Gravity guided the gas along routes carved by dark matter, like water flowing through a system of pre-dug channels. The gas didn't create its own pattern. It simply followed the blueprint that dark matter had already established. As the gas fell into these halos, it compressed and heated, and in the densest regions it eventually cooled enough to collapse further, forming the first stars and then the first galaxies. The overall pattern of where galaxies appear across the universe is therefore not determined by the luminous matter we can see, but by the underlying dark scaffolding that quietly organised the entire layout. As more matter accumulated in some regions, a larger pattern began to emerge. Dark matter didn't just form isolated clumps scattered evenly across space. Instead, it created a network, a web of connected structures. Elongated streams of dark matter and gas formed between the densest regions, creating what astronomers call filaments. These filaments are like the main supply corridors in a city's infrastructure plan, long, relatively broad routes that connect major hubs and through which material flows. They're not as densely packed as clusters, but they're far from empty. Gas streams along these filaments over cosmic time, gradually feeding the galaxy groups and clusters at the intersections. From a distance, filaments are subtle structures, easier to detect statistically across large surveys than to see as bright features in any one region, but they represent a core element of the cosmic web's architecture. Where multiple filaments intersect, gravitational wells become particularly deep. These intersections are where galaxy clusters form, the dense downtowns of the cosmic web, regions packed with hundreds or even thousands of galaxies all bound together by gravity. Clusters are immersed in massive dark matter halos and filled with extremely hot gas that emits X-rays. They represent the nodes of the cosmic network, the major hubs in a vast transport system, where everything nearby is gently funneled inward over billions of years. If you were to map the universe's matter distribution, clusters would stand out as the brightest, densest points, the places where the web's underlying design is most concentrated and most obvious. Between the filaments and clusters, you sometimes find even larger patterns, walls and sheets of galaxies spanning hundreds of millions of light years. These aren't solid structures in any sense. They're statistical patterns, regions where the density of matter is slightly elevated over enormous distances. Think of them as low-rise districts spreading between the densest hubs and the emptiest voids, transitional zones that help connect the web's various elements into a coherent whole. They're part of the universe's zoning map, showing how matter is distributed not just at individual points, but across vast volumes of space. These walls represent some of the largest known structures in the universe, yet they're also among the most difficult to perceive directly because their density contrast is so subtle. And then there are the voids, vast regions of space containing very few galaxies, stretching across hundreds of millions of light years. These aren't absolute vacuums, they contain dark matter, gas, and a scattering of isolated galaxies, but they're remarkably underdense compared to the rest of the universe. In the planning metaphor, voids are like large plots that simply never got developed. No highways were built through them, no major junctions formed within their boundaries. The same initial fluctuations that created dense regions necessarily left other regions underdense, and as gravity amplified these contrasts over time, the low-density regions expanded into voids. They provide the negative space that defines the cosmic web, the empty volumes that make the filaments and clusters stand out by contrast. This entire structure didn't spring into existence suddenly. The cosmic web grew gradually over billions of years through a process cosmologists understand quite well. As the universe expanded, gravity slowly amplified the original density ripples. Regions that started slightly overdense attracted more matter and became denser still. Regions that started slightly underdense lost matter to their surroundings and became emptier. Dark matter halos merged when they encountered each other, forming larger halos. Filaments thickened as more gas flowed along them. Clusters accreted more galaxies over time, growing from small groups into massive congregations. Voids expanded as matter drained from them into surrounding structures. Computer simulations show this as a gradual sharpening of patterns. What begins as a noisy, nearly uniform distribution of matter slowly evolves into a clearly defined network, like a faint sketch being traced over repeatedly until the lines become bold and unmistakable. These numerical simulations are essential tools for understanding the cosmic web. Cosmologists set up virtual universes on supercomputers, starting with initial conditions that match the early universe. Small density fluctuations in a mix of dark matter, ordinary matter, and dark energy, all expanding according to the equations of general relativity. Then they let the simulation run forward in time, allowing gravity and expansion to evolve the system. The results are remarkable. Three-dimensional structures of halos, filaments, and voids that closely resemble what telescopes observe in the real universe. These simulations act like model blueprints or proof-of-concept designs. If the input physics is correct, the large-scale pattern that emerges after billions of simulated years should match the actual cosmic web. And it does, providing strong confirmation that cosmologists understand the basic processes at work. Observationally, astronomers reconstruct the cosmic web through massive galaxy surveys. Modern telescopes can measure the positions and distances of hundreds of thousands or even millions of galaxies. The position on the sky is straightforward to measure, but distance requires determining each galaxy's redshift, the stretching of light caused by the universe's expansion. Higher redshift generally means greater distance. When astronomers plot these galaxies in three-dimensional space using their coordinates and redshifts, the cosmic web emerges clearly from the data. Filaments, walls, clusters, and voids all become visible as patterns in the distribution of points. To astronomers, these surveys are completed site plans, collections of dots on a coordinate grid that trace the underlying structure in a way the human eye and brain can immediately recognize as organized rather than random. There's a complication though. We don't see dark matter directly, we only observe its gravitational effects. The galaxies we count in surveys are traces of the underlying dark matter distribution, but they're not perfect traces. Galaxies form more readily in certain types of dark matter halos and certain environments, a property astronomers call bias. A galaxy survey doesn't show the dark matter web directly. It shows where galaxies chose to form within that web. Cosmologists calibrate this bias using simulations and observations, developing models that account for the relationship between visible galaxies and invisible dark matter. The result is a layered set of blueprints, one map showing the distribution of luminous matter, another inferred for the distribution of dark matter, and both carefully aligned to show how the visible universe reflects the invisible scaffolding beneath it. Dark energy also plays a role in shaping the cosmic web, though more subtly. Dark energy is a mysterious component of the universe that drives accelerated expansion, causing space itself to stretch faster and faster over time. While gravity works to pull matter together into structures, dark energy works against it by expanding the underlying space. In the universe's early history, gravity dominated and structures grew rapidly. But as dark energy's influence became more pronounced over billions of years, it became harder for new large-scale structures to form. In planning terms, it's as if the grid of space itself is stretching, making it increasingly difficult to build new neighborhoods or expand existing ones. Most of the cosmic web we see today was laid down before dark energy's influence became dominant, during the era when gravity could still effectively organize matter on the largest scales. Even today, the cosmic web is not a static structure. Gas continues to flow along filaments into galaxies and clusters, providing fresh material for ongoing star formation. This inflow isn't violent or dramatic. It's a slow, steady supply through cosmic pipelines. Simulations show cold gas streams feeding galaxies along filaments, while hot gas accumulates in the massive halos around galaxy clusters. The web supports these ongoing flows, acting as the infrastructure through which material is delivered to where stars can form. The pattern of the web itself doesn't change rapidly anymore. The major filaments and clusters are established, but matter still moves through the established channels, and galaxies still grow and evolve within their assigned neighborhoods. A galaxy's location in the cosmic web significantly affects its properties and evolution. Galaxies in dense cluster environments tend to be older, redder, and depleted of gas. They've undergone numerous interactions with neighbors, experienced ram pressure stripping as they move through hot intra-cluster gas, and exhausted their reserves of star-forming material. Galaxies along filaments often show more active star formation, supported by fresh gas flowing in from the cosmic web. Void galaxies, isolated from the main flows of matter, evolve more slowly and independently. They experience fewer mergers, accumulate gas more gradually, and can maintain distinct star formation histories. In the zoning language we've been using, different districts of the cosmic web encourage different architectural styles. The environment a galaxy inhabits shapes what it becomes. Astronomers have multiple methods beyond simply counting galaxies to map the cosmic web. Weak gravitational lensing provides one powerful technique. The gravity of dark matter concentration subtly distorts the light from more distant galaxies, bending it along its path. By measuring these tiny distortions in the shapes of background galaxies across large areas of sky, cosmologists can create maps of the total mass distribution, including the invisible dark matter. X-ray telescopes reveal hot gas in galaxy clusters and along some filaments, while radio observations can detect the same gas and even trace magnetic fields. These different techniques provide complementary views, mass maps, gas maps, galaxy maps, all of which can be stacked together. When they all show the same underlying web-like pattern, confirming that the structure is real and not an artifact of any single observational method. The cosmic web also has a history that astronomers can observe directly. Because light takes time to travel across the universe, looking at distant objects means looking back in time. By observing galaxies and structures at different redshifts, astronomers effectively see snapshots of the cosmic web at different ages. The youngest, most distant universes observable show a more uniform distribution of galaxies with less pronounced structure. The web is still forming, the patterns still emerging from the initial noise. Older universes, closer to our present day, display increasingly clear networks of filaments and clusters. Comparing these snapshots across cosmic time allows astronomers to test their models of structure formation, checking whether the theoretical blueprint model matches the actual construction schedule the universe followed. Despite the success of the cosmic web model, many details remain under active investigation. How feedback from supernovae and active galactic nuclei redistributes gas within and between halos is not fully understood, yet it significantly affects how galaxies form along the web. How the smallest dark matter halos, those too small to form bright galaxies, populate filaments and voids is still being mapped out. What the web looks like in extremely low-density regions, where finding and observing galaxies is difficult, requires better data. These are the fine print annotations in the planning documents, small notes and revisions added as new observations refine the existing maps. The broad picture is clear and well established, but the details continue to sharpen with each new survey and simulation. As you settle into sleep tonight, you can let your mind rest on this image. The cosmic web is not something visible to the naked eye, not something you could see even with the most powerful telescope if you looked at just one small patch of sky. But it underlies everything. Every galaxy, including our Milky Way, sits within this vast, mostly invisible framework. Dark matter halos provide the foundation. Filaments form the corridors. Clusters mark the intersections. Voids define the empty spaces. Together they create a structure of almost unimaginable scale, spanning billions of light years, connecting every part of the observable universe into a single coherent network. The universe is not random chaos. It's a large, slow construction project whose main plans were drawn up in the first moments after the Big Bang, when tiny quantum fluctuations were imprinted on space itself. Those fluctuations became the surveyor's marks, the initial guidelines that gravity would follow. Dark matter laid the invisible scaffolding. Ordinary matter filled in the visible structures. Dark energy stretched the canvas. And now, nearly 14 billion years later, the project is mostly complete. The cosmic web stands as it is, a faint, sprawling network of neighborhoods, roads, and empty lots stretching farther than the mind can easily grasp, steadily expanding in the dark. This is the architecture of the universe on its largest scale. Not built by any intelligence, not designed by any mind, but assembled gradually through the simple, patient work of gravity acting on matter over cosmic time. The filaments connect clusters that are themselves made of galaxies, which contain billions of stars, some with planets, some perhaps with observers looking out and wondering about the structure they inhabit. From our vantage point within it, we can barely perceive the web, but with telescopes and surveys and simulations, we've learned to map it, to understand it, to see the underlying order that gravity created from those ancient tiny ripples. And so the universe is not a featureless expanse. It has texture, structure, organization. It has neighborhoods where galaxies crowd together and vast expanses where they are scarce. It has highways of dark matter along which gas flows, and intersections where matter accumulates into the densest structures known. It has a history, a present state, and a future. As dark energy continues to accelerate the expansion of space, the web will stretch further, new structures will become harder to form, existing structures will become more isolated from one another as the space between them grows. But the basic pattern is set now, the blueprint fully realized. The cosmic web as it exists today is the architecture we live within, the framework that holds galaxies in their places and channels matter through the universe. Close your eyes and picture it if you can, not the bright galaxies themselves, which are merely lights marking nodes and paths, but the invisible web of dark matter beneath them. Imagine pulling back farther and farther from our galaxy, from our local group, from our local supercluster, until you can see the full three-dimensional network. Filaments stretching in all directions, clusters glowing at junctions, voids opening as dark empty spaces, walls spanning distances that light takes hundreds of millions of years to cross. All of it connected, all of it grown from the same initial conditions, all of it slowly evolving as the universe ages and expands. This is the landscape on the larger scale, the final zoning map of the cosmos, showing where matter congregated and where it didn't, which routes gravity carved out and which regions remained sparsely populated. It's a quiet story, lacking drama or sudden events, but it's the story of how the universe organized itself into the structure we observe today. The blueprint was drawn long ago in those first moments. Gravity did the slow work of construction. Dark matter provided the foundation. Ordinary matter filled in the details. And now the cosmic web spans the observable universe, a testament to simple physical laws operating over immense scales of space and time. As the universe continues expanding and you drift towards sleep, let this thought settle. We are part of this structure, embedded in it, subject to its organization. Our galaxy lies within a filament connected to a small cluster in a region between larger voids. We are not at a special location, but we are at a comprehensible one, a point within a vast network that has been mapped, studied, and understood through observation and theory. The cosmic web is both the largest structure we know, and in some ways, one of the simplest. It follows from basic principles: gravity, expansion, initial fluctuations, and time. From those ingredients, the universe built itself a framework, and within that framework, everything else, stars, planets, and observers, emerged. Sleep well in this knowledge. The universe has structure, it has order on the larger scales, and that order, impersonal and vast though it is something we have learned to see, to map, and to understand. The cosmic web stretches across billions of light years, mostly invisible, forever expanding, quietly holding the visible universe in its gravitational embrace. It is the largest blueprint ever drawn, and we have learned to read it. As you rest with that image of the cosmic web in mind, consider how remarkable it is that we've come to understand this structure at all. For most of human history, the universe beyond Earth was a mystery written in lights that moved across the night sky, according to patterns we could observe but not explain. The idea that galaxies, entire islands of billions of stars, even existed is barely a century old. The realization that these galaxies are not scattered randomly, but arranged in an enormous web-like structure is younger still, emerging only in the last few decades as technology allowed us to map millions of galaxies across vast distances. We live in perhaps the first generation of humans who can look up at the night sky and understand, at least in broad strokes, the architecture that organizes everything we see. The discovery of the cosmic web was gradual, built on layers of observation and theory. Early hints came from galaxy surveys in the 1970s and 1980s, when astronomers began plotting the positions of galaxies in three-dimensional space. What they found surprised them. Galaxies weren't distributed uniformly or even in simple clusters. Instead, they formed elongated chains and sheets, with curious empty regions between them. One of the most famous early discoveries was the Great Wall, a vast sheet of galaxies stretching across hundreds of millions of light years. Later surveys found similar structures, the Sloan Great Wall, even larger, the Hercules Corona Borealis Great Wall, larger still. Each new survey pushed the scale of known structures higher, revealing that the universe's architecture operated on scales far beyond what anyone had initially imagined. These observations presented a puzzle. Why would gravity create such patterns? Why filaments and walls and voids instead of a more uniform distribution or simple clustering? The answer came from understanding how structure grows from initial conditions. If you start with a perfectly uniform distribution of matter, gravity has nothing to work with. Every region pulls equally on every other region and nothing happens. But start with tiny variations, and gravity has something to amplify. Dense regions pull matter from their surroundings, growing denser while creating voids nearby. But the process isn't spherically symmetric, because the initial fluctuations aren't either. They have shape, orientation, and scale. Some regions are elongated, some are sheet-like, some are more compact. Gravity amplifies these shapes as it amplifies the density contrasts, leading naturally to filaments, walls, and nodes. Computer simulations made this clear in a way that mathematical equations alone could not. When cosmologists ran their first large-scale simulations in the 1980s and 1990s, feeding in the parameters of the universe and letting gravity evolve matter forward in time, they saw the cosmic web emerge spontaneously from the calculations. No one programmed in filaments or voids. These structures arose naturally from the physics. The simulations showed matter streaming along gravitational gradients, collecting in elongated patterns, forming dense nodes at intersections. When compared to actual galaxy surveys, the match was striking. The simulated universe and the real universe showed the same kinds of structures on the same scales. This was powerful confirmation that the theoretical framework was correct, but understanding the web requires understanding what fills it and what drives its evolution. Dark matter dominates the mass budget, making up about 85% of all matter in the universe. This invisible substance doesn't interact with light, which is why we call it dark, but it does interact gravitationally. In fact, in the early universe, dark matter was free to respond to gravity before ordinary matter could. While ordinary matter was still coupled to photons in a hot, opaque plasma, dark matter was already beginning to clump. This gave it a head start in forming structures. By the time ordinary matter finally decoupled from photons and could freely fall into gravitational wells, an event we observe as the cosmic microwave background, dark matter had already sketched out the basic pattern. Ordinary matter simply followed where dark matter led. This explains why the cosmic web is first and foremost a dark matter structure. The filaments, halos, and voids are primarily composed of dark matter. Galaxies trace this structure because they form where the dark matter is concentrated, but they represent only a small fraction of the total mass. If you could somehow see dark matter directly, the cosmic web would appear much more prominent and continuous than it does in galaxy surveys. The galaxies are like streetlights along highways. They show you where the roads are, but most of the road exists between the lights, invisible in the darkness. Dark energy enters the story later, becoming significant only when the universe was several billion years old. Before that, the universe's expansion was decelerating due to gravity. Matter was pulling back on the expansion, slowing it down, which allowed structures to grow efficiently. But as the universe expanded and matter became more dilute, the influence of dark energy, a property of space itself, began to dominate. Dark energy drives accelerated expansion, causing space to stretch faster over time. This has profound implications for structure formation. In an accelerating universe, it becomes progressively harder for gravity to pull matter together across large distances. The expansion works against gravity, pulling regions of space apart faster than gravity can draw them together. This means the cosmic web we see today is essentially frozen in its large-scale pattern. The major filaments and clusters formed during the era when gravity could still overcome expansion on those scales. New clusters can still form through mergers of existing structures, and galaxies can still fall into clusters along established filaments, but entirely new large-scale structures are no longer forming. The expansion has outpaced gravity's ability to organize matter on the larger scales. In a sense, the cosmic web is a fossil from an earlier epoch, a record of structure formation during the first several billion years of the universe's history, now preserved and slowly stretched by accelerating expansion. Yet within this frozen large-scale pattern, smaller-scale activity continues. Galaxies still form stars, still merge with neighbours, still evolve. Gas still flows along filaments, feeding new star formation. galaxy clusters still accrete new members from surrounding regions. The web provides the infrastructure within which these processes occur, channeling matter and influencing evolution without itself changing dramatically. It's like a city whose major highways and districts were laid out long ago and now define how traffic flows and where development happens, even though individual buildings continue to rise and fall. The role of gas in the cosmic web deserves particular attention. While dark matter defines the overall structure, ordinary matter, primarily hydrogen and helium gas, is what we actually observe in most contexts. This gas behaves differently from dark matter. It can collide with itself, converting kinetic energy into heat. It can cool by radiating that heat away. It can collapse into dense clouds and form stars. All these processes affect how gas distributes itself within the dark matter scaffolding. In low-density regions like filaments, gas may remain diffuse and warm, detectable only through its absorption of light from background sources. In high-density regions like clusters, gas becomes extremely hot, millions of degrees, and emits brightly in X-rays. This hot intra-cluster gas is one of the most massive components of galaxy clusters, often outweighing all the stars in all the galaxies in the cluster combined. It fills the space between galaxies, trapped by the cluster's gravitational well, heated by the energy of galaxies falling in, and by shocks propagating through the gas. When new galaxies fall into a cluster, they plough through this hot gas, which strips away their own cooler gas through ram pressure, the same effect you feel when you stick your hand out a car window. This process transforms galaxies, shutting down their star formation and changing their appearance. A blue star-forming spiral galaxy that falls into a cluster can become a red, passive elliptical galaxy over time, its gas stripped away, its star formation choked off. The cosmic web doesn't just organize where galaxies are, it influences what kinds of galaxies they become. Filaments too contain gas, though it's harder to observe. The gas in filaments is typically warm, tens of thousands to hundreds of thousands of degrees, too cool to emit X-rays efficiently, but too hot to form stars. This gas remains largely invisible, except when illuminated by bright background sources or when observed through its subtle absorption signatures. Yet this filament gas represents a significant fraction of the universe's ordinary matter, perhaps as much as half of all the baryons that aren't locked up in stars or dense gas clouds. It's part of what astronomers call the missing baryon problem, the challenge of accounting for all the ordinary matter that should exist based on measurements of the early universe. Much of it appears to be hiding in the warm gas of cosmic filaments, too diffuse to easily detect but collectively massive. The flow of gas along filaments into galaxies is crucial for understanding how galaxies grow and form stars over cosmic time. Stars form from cold, dense gas, but galaxies can exhaust their internal gas supplies relatively quickly, within 1 billion years or so if star formation proceeds unchecked. Yet we observe galaxies forming stars continuously over much longer timescales. This means they must be replenishing their gas from external sources. Filament inflow provides that replenishment. Cold gas streams along filaments, funneled by gravity into galaxy halos, where it can cool further and eventually form stars. This process is most efficient for galaxies connected to filaments, which may explain why such galaxies show more ongoing star formation than similarly sized galaxies in voids. Void galaxies present an interesting contrast. These isolated systems, far from the main filaments and clusters, evolve in relative solitude. They experience fewer mergers, accumulate gas more slowly, and maintain lower star formation rates. Yet they're not entirely quiescent. Some void galaxies show recent star formation, suggesting they're not completely cut off from gas supply. Perhaps they're slowly accreting material from the diffuse gas that does exist in voids, or perhaps they're recycling gas from earlier generations of stars. The differences between void galaxies, filament galaxies, and cluster galaxies demonstrate how environment shapes evolution. The cosmic web provides different conditions in different regions, and galaxies adapt to those conditions in observable ways. This environmental dependence extends to galaxy properties beyond just star formation. Cluster galaxies tend to be larger, more massive, and older on average than field galaxies. They've had more opportunities to merge with neighbours, growing through accretion. They've undergone more interactions that can trigger bursts of star formation or feed supermassive black holes at their centres. Their shapes are affected. Cluster galaxies are more likely to be elliptical or lenticular. with smooth light distributions and little cold gas, while field galaxies are more often spirals with disks and active star formation. Even the dark matter halos around galaxies differ depending on location. Cluster galaxies sit in halos that have been tidally stripped and shaped by interactions, while isolated galaxies retain more extended, undisturbed halos. The cosmic web also affects galaxy spins and orientations in subtle ways. Studies have found weak correlations between galaxy properties and the direction of nearby filaments. Some galaxies seem to have their spin axes aligned with or perpendicular to filaments, depending on their mass and location. These correlations are statistical rather than deterministic. Not every galaxy follows the pattern, but they suggest that the large-scale structure imprints itself on smaller-scale properties. The way matter flows along filaments can influence how galaxies acquire angular momentum, which in turn affects their final shapes and spin directions. Even something as fundamental as which way a galaxy rotates may have been influenced by its position in the cosmic web. Observing the cosmic web across cosmic time has revealed how it evolved and continues to evolve. At high redshifts, looking back to when the universe was only a few billion years old, the web appears less mature, structures are less pronounced, filaments are thinner and less well defined, clusters are smaller and less rich in galaxies. This is exactly what models predict. The web grows over time as gravity amplifies initial density contrasts. By comparing observations at different epochs with simulations run to the same epochs, astronomers can test whether the growth rate matches expectations. So far, the agreement is good, providing yet more confirmation that the basic picture is correct. Yet there are puzzles. Some observations suggest that structures might be growing slightly slower than the simplest models predict, which could indicate something subtle about dark energy or gravity on large scales. Other observations hint at unexpectedly large structures that seem difficult to form in the available time given the measured density fluctuations in the early universe. These potential tensions are being investigated carefully. They could be statistical flukes, observational systematics, or genuine hints that the standard model needs refinement. This is how science progresses. The broad framework is established, but the details are continually tested and refined as data improves. The techniques for mapping the cosmic web continue to advance. Early surveys measured redshifts one galaxy at a time, a painstaking process that limited sample sizes. Modern surveys use spectrographs that can measure hundreds of galaxy redshifts simultaneously, covering large areas of sky in reasonable observing time. The Sloan Digital Sky Survey, one of the most influential projects in modern cosmology, mapped millions of galaxies, revealing the cosmic web in unprecedented detail. Newer surveys like the Dark Energy Spectroscopic Instrument are pushing even further, aiming to map tens of millions of galaxies across cosmic time. Each new dataset sharpens the picture, revealing finer structures and extending the map to earlier epochs. Complementary techniques add depth to the picture. Weak gravitational lensing surveys map the total matter distribution, both dark and luminous, across large areas. These mass maps show the cosmic web as seen through its gravitational effects rather than through its luminous traces, providing an independent view. X-ray surveys reveal the hot gas in clusters and filaments, while radio surveys can detect cold gas, neutral hydrogen, and even magnetic fields threading through the web. Combining all these observations creates a multi-wavelength, multi-messenger picture of the cosmic structure, each technique sensitive to different components and physical conditions. The future promises even more detailed views. Upcoming telescopes and surveys will map the cosmic web at higher redshifts earlier times, revealing how the web looked when it was just beginning to form. They'll measure galaxy properties within the web in greater detail, tracking how environment influences evolution across billions of years. They'll measure the velocities of galaxies, not just their positions, revealing how matter flows through the web, and they'll map the web on smaller scales, down to individual galaxy groups and even smaller halos, connecting the largest cosmic structures to the scales where individual galaxies live. As these observations accumulate, they feed back into theory. Simulations become more sophisticated, including not just dark matter, but also gas physics, star formation, feedback from supernovae and black holes, magnetic fields, and cosmic rays. These advanced simulations can predict not just where structures form, but also what kinds of galaxies should populate them, what their properties should be, and how they should evolve over time. Comparing these predictions to observations tests our understanding of both the cosmic web and the galaxy formation processes that occur within it. When predictions and observations agree, confidence grows. When they disagree, it points to missing physics or incorrect assumptions that need to be addressed. One area of active research is the connection between the smallest dark matter halos and the galaxies that inhabit them. Dark matter theory predicts that halos should exist across a vast range of masses, from galaxy clusters down to masses far smaller than any visible galaxy. But not every dark matter halo contains a visible galaxy. Below certain mass thresholds, the gas in a halo may be too warm to collapse and form stars, or feedback from early stars may blow the gas out, preventing further star formation. Understanding exactly where the threshold lies and how it depends on environment and cosmic epoch is crucial for connecting the dark matter web to the visible galaxy distribution we observe. Another frontier is understanding the warm-hot intergalactic medium, the gas that fills filaments in the regions between structures. This gas contains a large fraction of the universe's baryons but is difficult to detect. It's too hot to form stars, too cool to emit X-rays efficiently, and too diffuse to show up in most observations. Yet it's there, predicted by simulations and detected through subtle absorption signatures in the spectra of distant quasars. Mapping this gas would complete our sensors of matter in the cosmic web, revealing the full extent of the structure, not just the parts traced by galaxies and hot cluster gas. The cosmic web also connects to fundamental questions about the nature of dark matter and dark energy. If dark matter is made of particles, those particles must have properties that allow structure formation to proceed as observed. Too much interaction between dark matter particles, for instance, would smooth out small-scale structure, contradicting observations. Too little, and we might see more small-scale structure than observed. The cosmic web thus constrains dark matter models. Similarly, the growth rate of structure over cosmic time depends on dark energy's properties. If dark energy has evolved over time rather than remaining constant, the cosmic web should show signatures of that evolution. Precision measurements of structure at different epochs can therefore test models of dark energy, turning the cosmic web into a laboratory for fundamental physics. There's something profoundly satisfying about the cosmic web as a concept. It represents order emerging from simplicity. The rules are straightforward. Gravity attracts, space expands, matter responds to both, but the consequences are rich and complex. From nearly uniform initial conditions, the universe constructs an intricate network spanning billions of light years. No intelligence designed it, no plan guided it, yet it has structure, regularity, and beauty. It's a reminder that nature, operating through physical law alone, can create complexity and organization on scales that dwarf human experience. Consider the path that matter took to arrive at its current distribution. In the beginning, in the unimaginably hot and dense state of the early universe, matter and energy were nearly uniform. Quantum fluctuations in the inflation field, tiny, random variations at the quantum scale, were stretched to cosmic sizes by exponential expansion. These fluctuations seeded all subsequent structure. As the universe cooled and expanded, these seeds grew under gravity's patient influence. Dark matter clumped first, forming halos. Gas followed, forming stars and galaxies. Over billions of years, small structures merged into larger ones. Halos joined into groups, groups into clusters, clusters into superclusters connected by filaments, and through it all, space continued expanding, stretching the web to its current vast dimensions. Your own atoms participated in this cosmic journey. The hydrogen in your body was forged in the Big Bang, part of that initial nearly uniform distribution. It spent billions of years flowing through the cosmic web, perhaps falling into a filament, then into a galaxy, then into a molecular cloud, and finally into a star. That star lived and died, returning enriched material to the interstellar medium. The carbon, oxygen, nitrogen, and other heavy elements in your body came from such stellar processing. These atoms drifted through space again, eventually collapsing into a new generation of stars and planets, including our Sun and Earth. You are made of matter that once flowed through the cosmic web, subject to the same gravitational forces, the same expansion, the same grand pattern that organizes the universe on its larger scales. In that sense, we're not separate from the cosmic web. We are part of it. Our galaxy is a node within it. our local group a small cluster connected to larger structures. The matter we're made of came from it. Our evolution as a species occurred within a galaxy shaped by its location in the web. Everything about our existence is contextual to this structure, embedded in this framework. Understanding the cosmic web is, in part, understanding our own context within the universe, seeing the larger architecture that contains us. As you drift closer to sleep, let this awareness settle. The universe is vast beyond imagining, yet comprehensible. Its largest structures follow from simple principles, played out over enormous spans of time and space. The cosmic web, filaments, clusters, walls, voids, is the natural outcome of gravity, expansion, and initial fluctuations. We live within this structure, embedded in it at every scale, from the atoms in our bodies to the galaxy we inhabit to the supercluster within which that galaxy resides. And perhaps most remarkably, this structure is knowable. Through patient observation, careful measurement, and theoretical insight, we have learned to map the cosmic web, to understand how it formed, to predict how it will evolve. We can run simulations that recreate it. We can measure its properties across billions of light years. We can see it at different ages by looking at different distances. We can connect its largest features to tiny fluctuations in the infant universe. The cosmic web is not forever beyond our grasp. It is something we have come to understand in this brief moment of cosmic history through the application of human curiosity and intelligence. Rest now in this knowledge. The universe has architecture. It has order. It has a structure that connects everything within it into a single coherent whole. And you, small as you are, distant as you are from most of it, are part of that whole, made of its matter, subject to its laws, comprehensible within its context. The cosmic web stretches across the observable universe, vast and mostly invisible, forever expanding, quietly holding everything in its gravitational embrace. Sleep well, knowing that even the largest structures in existence follow patterns we have learned to understand. The next story is about to begin. Please relax and enjoy.